Hello everyone and welcome to MV Tutors. I'm Tsulu and we are looking at the chemistry paper. Okay, so today we're going to do question 1. I'm going to do question 1 with you guys. And yeah, if you have any comments, please do comment below. Any suggestions, any questions at all, please do ask. Okay, so let us get to it. It's actually the 2021 paper. And let's see what they're asking for question 1. Alright, so, 1.1. Okay, so it says, which one of the following compounds has hydrogen bonds between molecules? Is it A, pentanol? So the al will tell you that it's an aldehyde. Okay, I'm just going to draw out the structural formula for you so that you can see the difference. Okay, so there we are with 1.1. We have pentanol. So pent meaning there are 5 carbons, okay, and it's an aldehyde, so we have that double bond to oxygen and hydrogen at the end there. Okay, I'm just gonna draw lines indicating the hydrogens there just so that you can see what's happening. Okay, so is it pentanol? Let's see. Pentan 2-one, also 2-pentone. Pentanon. Oh my gosh, not 2-pentone, 2-pentanon. That's basically a ketone, okay, still with 5 carbons to it. A ketone and an aldehyde are actually isomers, right? So more like positional isomers. Okay, so that was A. Okay, now B, how is that going to look? Okay, still you have 5 carbons, okay, but on the second carbon we're going to have our double bond there. Okay, so whichever if second comes this side or comes, I'm just going to put it there. Let's just see, that's 1, 2, 3, 4, 5. So on the second one we have our double bond there and the rest is as normal. Okay, so currently hydrogen bonds, not yet. Okay, let's see, pentanoic acid. So that is a carboxylic acid, and how I remember that, Cu actually. I don't know if that makes sense, but you have a double bond to oxygen, then you have a hydroxyl group there. Okay, there we have our hydrogen bond. But let's finish everything. Okay, so Cu, COOH, that is representative of the carboxylic acids. Okay, and yeah, that seems to be the winner so far because of the hydroxide there. We have hydrogen bonding there, but let's see. Now we have methyl butanoate. Okay, so the methyl part will actually be the alcoholic part. So you had methanol and butanoate, that will be the carboxylic part. This is an ester, by the way. So D, it's an ester, where initially you had methanol and butanoic acid. Okay, so now you have methyl butanoate. And how that would look, okay, you would actually have your oxygen there, carbon, and then you have your other carbons there, okay, and the rest of the hydrogens. Okay, so an ester is as a result of a carboxylic acid and alcohol, and they produce an ester with water. Okay, so here we don't really have hydrogen bonding, so the winner would be C. Okay, so C would take the prize there. Yeah, I don't think I can sketch this. So yeah, C is the answer. I'm going to indicate it with a different colored pen. And yeah, there we have it, C. Okay, let's move on to 1.2. You don't really have to go through it the long way. I just want you to see where I got the answer from. Now it says, to which homologous series does a compound with molecular formula C6H12O2 belong to? Okay, so again here, So we have a ketone, right? And then we have what? Alcohols. We have aldehydes. And we have carboxylic acid. Okay, guys, here we had a ketone. For the first, I'm going to use 1.1 as an example. So A was pentanol, which is an aldehyde, and B was pentan 2-one or 2-pentanon, which is a ketone. And if we have a look at both of them, okay, so okay, we have C5 here, but I mean the general formula that we see here, I'm just going to write it here. So we have a general formula of C6H12O2. Okay, so we can see it's actually CnH2n and then just O2. Okay, so if you look at the aldehyde there, okay, you only have one oxygen, okay, one oxygen atom, okay. If you have a look at the ketone, you only have also just one oxygen atom. If you have a look at an alcohol, okay, an alcohol only also has one oxygen atom. Did I say molecule last time? It's actually atom. One oxygen atom. Okay, so ketone, alcohol, aldehyde, that's not going to work. But if you look at your carboxylic acid, you do have two oxygen atoms. Even if you were to look at your ester, you also have two oxygen atoms. So yeah, so our answer there is going to be D, which is carboxylic acid. Okay, and actually a carboxylic acid and an ester are actually isomers of each other. They have the same general formula, or rather molecular formula here. Okay, so we have our answer. It's D. It's the carboxylic acid. Okay, now we look at 1.3. Okay, my thingy doesn't want to go up. All right, so yeah, there you go. 1.3, which functional groups are involved in the formation of esters? Okay, I've mentioned this, guys. You have your alcohols and your carboxylic acids. So let's go through the options. So you have a formyl and carbonyl. Hydroxyl, yeah, remember what is it? Alcohol, OH, so hydroxyl. But carbonyl, new. Hydroxyl, carboxyl, yeah, that seems about it. D, carbonyl, carboxyl, no. Definitely has to be hydroxyl because of the OH from the alcohol, and carboxyl because of the carboxylic acid. So our answer therefore will be C. Alrighty. And then we get to 1.4. So the equation below represents a reaction at equilibrium. Okay, so we have, I forgot the actual names, chromate and dichromate. Yes, we have chromate there, that's yellow, and dichromate there, which is orange. Okay, so now in this equation or this formula, this reaction at equilibrium, so what happens there? You have this yellow chromate, né? The thing is, the moment you add an acid, which is your H plus, né? Remember H plus or H3O, that is, more representative of your acid. If you're gonna add more acid to it, okay, so let me just put it this way. If you're gonna add H plus, né, ions there, you are actually increasing the reactants. So what's going to happen? You have disturbed the equilibrium, right? And according to Le Chatelier's principle, in order to form new equilibrium, the equation, or rather the reaction is going to shift to the left. Sorry, to the right. It's going to shift to the right, right? And it's going to increase the product, okay? So in order to counteract you adding an acid or your H plus atoms, or rather ions, it's going to increase your products. And if you increase your product, your color will be more orange. Okay, so already we know if we increase the acid side or increasing the hydrogen ions. Now, if you're gonna, I should actually be looking at the options, né? Let's go with A. Let's see what A says. You are adding sodium hydroxide pellets. Sodium hydroxide is a base. So if you're adding to a base, you are actually taking away the hydrogen ions. And if you take away the hydrogen ions, which are on your reaction side, okay, your equilibrium is going to move to the right, to the left. What's wrong with me today? It's going to go to the left, guys, okay? So therefore, your reactants are going to increase. Just to balance things, just using Le Chatelier's principle. So your reactants are going to increase. And if they increase, you're going to have more of a yellow color. Okay, so that's basically what's going to happen. Now, C and D talks about an increase and a decrease in pressure. Okay, normally when looking at Le Chatelier and what happens when you increase or decrease pressure, you need to ask yourself, do you have gases? This only applies to gases. And in our reaction here, you only have aqueous solutions as well as liquids. So C and D don't really count. But what is A? A is an addition of a sodium hydroxide, which is a base. Okay, we talked about a base here. Okay, this is what happens when you add a base. And then B talks about the addition of an acid. We already spoke about the acid there. Okay, so yeah, which one of the following will change the color of the mixture from yellow to orange? Definitely increasing the acid. Okay, if you increase the acid, you are adding more H plus ions. And if you're adding reactants, Le Chatelier's like, hold up, we got to balance this, we got to get a new equilibrium. And then on your product side, they have to increase. And if you increase in your products, your thing will become more orange. So therefore, B is the answer. The addition of the acid, hydrochloric acid there. So B, definitely it. C, it was it there. Okay, now let us go to 1.5. Okay. Consider the potential energy graph for the reaction below. Now it says the activation energy for the forward reaction in terms of P, Q, and R is... Okay, guys, so you have something like this. Okay. The activation energy is what is required to get this reaction going on, happening. So this is the activation energy. And the nice thing about having a catalyst is the catalyst actually lowers the activation energy. So the purpose of a catalyst is to lower the activation energy. So you don't need that much energy for this reaction to actually happen. Okay, but anyway, they're not asking about a catalyst here. I thought I should just add that as extra information. And because you see there's more energy required there for the reactants to finally turn into products, this is an endothermic reaction. Just putting it out there. But what they are asking, okay, what is the activation energy? So here we had Q, okay, and there we have P. So definitely our activation energy is going to be P. Sorry, let me just do this. It's actually going to be the difference between Q and P. Okay, so it will be Q minus P. And let's look for it there. If you look for it here on the options, you'll see that it's actually option D. Okay, so yeah, D it is. And then we get to 1.6. Alrighty. So it says a reaction reaches equilibrium in a closed container according to the following balanced equation. So here we have hydrogen and nitrogen, and we get ammonia. If you know it, that is like the Haber process, part of normally question 10. Yeah. So anyway, which one of the following changes will increase the value of the equilibrium constant? Now, do you remember the equilibrium constant? So equilibrium constant, that's Kc, right? Actually, it could be Kp because we're dealing with gases. Yeah, Kc if we just have aqueous solutions. So we have the concentration of the products over the concentration of reactants. That is the formula for the equilibrium constant. Now they want to know which one of the following changes will increase. So we want to increase the equilibrium constant. Okay, guys, if you are going to increase the reactants, the concentration of the reactants, your equilibrium constant is going to decrease. They are inversely proportional to each other. But if you, sorry, me and my many colors, if you're going to increase the products, because that is directly proportional to the equilibrium constant, your equilibrium constant is going to increase. So whatever you're going to suggest, you must make sure products are increasing. That is the one way of increasing the equilibrium constant. Now let's look. If you remove the product, ammonia, if you remove it, guys, we have nothing. So Kp is going to be 0. Your equilibrium constant is going to be 0. So definitely not A. Now, B, we are heating the container. Oh, by the way, let me just write it out. Okay, so we have, sorry, wrong colored pen. You'll be like, does it matter? Not really, but some of us, it really does matter which color we use. Okay, and then we have 2NH3, and all of those are gases. And an important thing they've told us that this is an exothermic reaction. Okay, if your enthalpy is less than 0, then this is it's an exothermic reaction. So here's the thing: an exothermic reaction, it gives off heat. Okay, it gives off heat there on the product side. So you already know A does not work. If you're going to remove the product, your equilibrium constant is going to be 0. Okay, if you heat the container, okay, you are adding heat to the container. By adding heat, it's like actually increasing your reactants. Okay, so adding heat, yeah, basically it's on the reactant side. If you're going to increase the reactants like we discussed, your equilibrium constant is going to go down, so that doesn't help. If you are cooling the container, okay, it's more on your product side. Okay, so this is where you heat the container, and this is where you're cooling the container. So by cooling it, guys, your products are going to increase, and that's what you want. So we have our I on C, but let's see, what does D say? Increasing the volume of the container. Yeah, that doesn't really apply to the equilibrium constant. Okay, so volume, no, not as much. That doesn't really do anything. Okay, so D is definitely out. And finally, our answer is going to be C, cooling the container. Okay, because it's an exothermic reaction. Yes, cooling will apply more to your product side. You're increasing the products, and C takes the prize. Okay, so cooling the container. Awesome. Now let us go to 1.7. Okay, so 1.7, sulfuric acid ionizes in water according to the following equations. Okay, so you have sulfuric acid, which is a liquid, plus the liquid water, and it gives you hydronium ions and HSO4. I think it's sulfuric acid, I'm not sure. Then you have HSO4 plus water gives you again hydronium ions and SO2 minus. So just, yeah. Now, consider the following statements regarding the ionization above. Okay, so you know you have your acid, which is sulfuric acid, right? And you're adding water. So basically water, it can act as both an acid and a base. In this case, because we already have an acid, water will act as a base. So one, it says H2O acts as a base in both reactions, and that is true. Okay, and then HSO4 acts as an ampholyte. An ampholyte is what water is. Okay, an ampholyte can act both as a base and as an acid. So yes, it's true, HSO4 can act as an ampholyte, but in this ionization, in these two equations, is it really acting as an ampholyte? And then it says SO4, 2 minus, is the conjugate base of H2SO4. Okay, so let's see. I'm just going to write the first equation down. Okay, where it starts with sulfuric acid. And that is a liquid plus water, which is a liquid, which then can be a forward and backward reaction. We have hydronium ions in aqueous solution, and we have HSO4 minus. Okay, so this is your acid, right? And that is your base. Okay, so now that will be your conjugate base, and that will be your conjugate acid. Okay, so now let's go back. We said water it is acting as a base in both reactions, which is true. Now let's go to the last one. SO4 2 minus is the conjugate base of H2SO4. Okay. Oh, H2SO4. So yeah, so H2SO4 is an acid here, and then HSO4 is a conjugate acid, okay? We're also going to have HSO4 as an acid, and then your last remaining one, which would be SO4 2 minus, that will be a conjugate acid. So 3 does not really work, guys. Okay, so 2, yeah, those are the options that I can think of. 1 and 2 is the one that's taking the prize at the moment. So we have an option A, which is 1 only. And then we have 1 and 2. Yes, so I would go for B in this case. Okay, because like I said, HSO4, it does act as an ampholyte in general. Okay, it can be a base and it can be an acid. However, in this case, yeah, actually, yes, it is a base in this case. It is a base for the first equation, but it's an acid in the second equation, so it does work in this case as well, not just in general, also in this case. So I will go with B. And if I'm wrong, y'all can correct me in the comment section. Okay, 1.8. Which one of the following reactions, when used in a voltaic acid, will give you a positive reading on the voltmeter? Okay, so this is where you consult your tables, table 4A and 4B, or is it 4B and C? Yeah, so you have magnesium. Okay, I'm just going to write them down. You have magnesium and you have zinc. Okay, then you have copper and silver. I'm sure there's a faster way of doing this, but I will just write it down so that you see where I got my stuff. And then we have nickel and we have iron. Okay, so what happened to these things? Magnesium, it started off as 2 plus and then it ended up as a solid. Okay, so it gained 2 electrons. Okay, so magnesium was reduced. Okay, meaning your zinc was oxidized. Okay, then we have copper, right? So copper then lost 2 electrons, so it was oxidized, and silver, they gained electrons, so it was reduced. Cobalt, it gained electrons, so it was reduced. And you have tin there, which was oxidized. Nickel, well, it gained electrons again, it was reduced. And iron there, it lost electrons, so it was oxidized. And then we have this formula, guys, on your formula sheet. Just gonna go all the way to the bottom. Okay, so your formula sheet here, it tells you that if you want to get the E of the cell, okay, or rather EMF, your electromotor, I forgot what the F stands for. Okay, so it would be, you can choose from these 3. Okay, so E cell is equal to E reduction minus E oxidation. I think I prefer that one. Okay, so we have E cell is equal to E reduction minus E oxidation. Okay, so yeah, let us go and have a look at these values and see which one is actually going to give us a positive value. Okay, so for magnesium, it was reduced. Let's see, where is magnesium? Have I passed it? Okay, there's magnesium. So it is negative 2,36. So I have negative 2,36 minus, and then zinc. Zinc was oxidized. There is zinc. Okay, so zinc is negative 0,76. So negative 0,76. Okay, guys, you have a very big negative number, and you're going to add to it a small positive number. So your result will be negative. Okay. Then we go to copper. Okay, Cu, I think it was 2 plus. Yeah, I think so. I think it is this one that we're looking at. Okay, so it has positive 0,34, but that was oxidized. So 0,34, and let's see the reduced part, which is silver. There is silver as 0,8. Okay, so this will be a positive value. I mean, I would stop here, but we just need to make sure with the other ones. Okay, so now cobalt. There is cobalt. It's negative 0,28. Negative 0,28 minus tin. So SN, there it is. It's 0,15 minus 0,15. So definitely you're going to get a negative answer there. And then nickel. Nickel is negative 0,27. And then minus iron. Iron, okay, there's one here, but this is not the one we're looking for. Okay, there's another one. There should be another one. So we have this iron, then we have that iron. Are those the only two? Oh, yes, that's the one that I'm looking for here. Okay, so we have 0,77. So this is definitely a huge negative number. So, yeah, guys, we're definitely going to go with B here. Okay, B again takes the crown. So, yep, let's go back to question 1. And yes. Oh, actually, no, the iron, I took the wrong one. It's just iron 3 plus. Okay, let's go back and check. Sorry, guys. Iron, yes, this is the one. But still, I mean, it's negative 0,06. So we are having minus 0,06. So we have a small negative 0,27 plus a very, very small value. It's still going to be negative at the end. So yeah, it's not really happening. Hey, so yeah, our answer is still B. Okay, and then yeah, almost there, guys, almost there. So now 1.9. Okay. Okay. Which one of the following statements is correct for an electrolytic cell? Okay, guys, I thought it would be best to just sketch out an electrolytic cell for you so that it is clear as to what's going on. So let's say you have your beaker there and you have your anode and your cathode. If you were to draw it, you would know that the positive side is on the anode and the negative side is on the cathode. Okay, the electrons are flowing from the anode to the cathode. So your anode is positively charged and your cathode is negatively charged. So I'm just going to write anode this side and cathode that side. So your cathode is actually reduced because you gain electrons, and your anode is oxidized. because you lose electrons. Okay, then you have your solution in there. Okay, and you have your ions inside, and yeah, obviously your negatively charged ions are gonna come closer to your anode, and your positively charged ions are gonna come closer to your cathode. Okay, and yeah, that's pretty much what it looks like. Now let's see. It says the anode is the positive electrode. Yes, it is. The cathode is the positive electrode. No, it is the negative one. Oxidation takes place at the cathode. No, reduction takes place there. Reduction takes place at the anode. No, oxidation takes place there. So yes, A is the only answer that's right. The anode is the positive electrode. Okay, so A takes it. All right, now we go back to our questions. The last one, question 1.10. Which one of the following shows the industrial process in which ammonia is a reactant and a product respectively? Okay, so remember the Haber process. We just wrote the equation. You have hydrogen, you have nitrogen, okay, and you therefore have ammonia. Okay, this equation is not balanced, but here in this case, ammonia is a product. Okay, and that is the Haber process. Then you have the contact process. There you're trying to get sulfuric acid. So no, we're not looking at that. But the Ostwald process, that's where you're trying to get nitric acid. So you are going to take your ammonia and add it with whatever to get nitric acid. I actually forgot. Yeah, I actually forgot with the Ostwald. I need to go and look in my notes what you added with. But yes, in this case, in the Ostwald process, it is a reactant. Okay, so it's a reactant in the Ostwald. And then it's a product with the Haber process. Okay, so reactant, we said Ostwald, so it could be A or B. And then your product, it is the Haber process. So yes, B is the answer for 1.10. And we are done. Yeah, it took quite a while, but it was fun. I hope you enjoyed it as well, and I hope you understood. Again, if you have any questions, comments, anything really you want to say to us, please do comment below. And if you do want a session, private session, do visit our website www.mvtutors, M for mom, V for van, mvtutors.co.za. Have yourself a great day further. Hello everyone, and welcome to MV Tutors. I'm Tolo, and I'll be looking at question 2 of the chemistry paper, June 2021. Okay, let's get to it. Alright, so the letters A to F in the table below represent 6 organic compounds. So A, we have methanoic acid, pentanol for B. C, we have C10H22, which could be decane. It's an alkane. 10 carbon atoms, so decane. D, we have a complicated one there. I would have to look at it quite closely to see what it's called. E, I see we have an OH, so it's an alcohol. And F, I see double bond to oxygen, so that is a ketone. Okay, so what I do, okay, I look at this table and I just write it out for myself the best way I know how to. Okay, so that when it's time for answering questions, I just flow. Okay, so A, we have methanoic acid. So you know that methanol just has 1 carbon. So with an acid, Cu, alright, so we have C double bonded to O and a bond to OH. Okay, so that's methanoic acid. And then B, we have pentanol. It is an aldehyde with 5 carbon atoms. We did discuss this in question 1. So yes, we have a double bond at the end there. and the rest are just hydrogen bonds. Did I just do that? Put an O there. It's supposed to be an H. I got too excited. Alright, so everything around a carbon atom, 4 bonds around a carbon atom, just make sure. So that's pentanol. And then C, we have, like I said, if you have a formula where you have CN, H2N plus 2, you know you have an alkane. So in this case, we have decane. It's weird when you say that. It's like decane. Okay, here, guys, we have how many carbon atoms? I'm going to straighten it out. So I'm going to straighten D out. So I'm counting 1, 2, 3, 4, 5, 6, 7, 8. I have 8 carbon atoms. Okay. And then so I have the first one, which is CH3, second one, H2, third one, H2, fourth one, I have a H and bromine atom. Then I have a fifth one, H2, and then again bromine atom, and then CH2, and then CH3. Okay, so if I were to look at this, I would number it from the right to the left. Okay, because this bromine is on the 4th carbon, but if I count this side, the bromine is on the 3rd carbon. So you want to choose the one that's like closest. So 1, 2, 3, 4, 5. So if I were to name this will be like 3, 5 di, because there are 2 bromine atoms. So dibromo. I would say dibromo. And we have 8 carbon atoms. 1, 2, 8, yes. Yeah, so 3,5 dibromo octane. Okay, so that's D. And then we have E. So E, we said that it's an alcohol because of the OH, and we have 1, 2, 3, 4, 5, 6. So it is hexanol. Okay, you could say 1 hexanol, but yeah. So if it's just hexanol left, you can assume yes, the OH bond, the hydroxide bond is on the 1st carbon. And if it's on the 1st carbon, it's like a primary alcohol. I haven't read the questions yet. I'm just gathering the information they gave us and just, synthesizing it. Okay, so if, what is that? I said it's a ketone because you have your double bond within. Okay, so it's like a secondary ketone. Okay, so it has 1, 2, 3, 4, 5. It's similar to the other one, so it's pent. Pentan 2, yes, one, or 2-pentanone. It's really up to you. Pentanone, pentanon. No master of pronunciation. All right, so now let's get to the questions, guys. We've analyzed the data given to us, and now we can answer. So now it says, write down the letters that represents the following. A ketone, okay, we just spoke about it. That is F, okay, 2.1.2. 2 compounds that are functional isomers. Okay, functional isomers. I think, and when I was doing question 1, I talked about positional isomers. Ketone and an aldehyde are functional isomers, the same as a carboxylic acid and an ester. Those are functional isomers because they are from different isomers. Sorry, they're from different. My husband. Sorry about that. So yes, functional isomers are in different functional groups. Okay, but they have the same molecular formula. All right. So 2 compounds that are functional isomers. For B, we have an aldehyde, okay, pentanol. All right, we even drew out the structure, yes. And then for F, we have a ketone, and those 2 are functional isomers. So it's B and F. Okay, cool. And then 2.1.3, a hydrocarbon. Okay, so methanoic acid, that is a carboxylic acid. Pentanol, that's an aldehyde. D, we have a hydrocarbon, right? Decane, the one. D, oh, that's C. C is the hydrocarbon. D, that is, it would have been a hydrocarbon, but you have bromine. Okay, and bromine is a halogen. So that's like a haloalkane. Okay, so that doesn't work. E is an alcohol. F is a ketone. So yeah, C, that is the one, the hydrocarbon. Okay, and now let's go to 2.2. So for compound D, okay, D, yes, we wrote it down. We had a look at it. So we can look at it further. So it says the homologous series to which it belongs. Okay, we talked about it. We can have a look at it again. There, D. Oh, we just actually mentioned it. It is a haloalkane. Okay, because it's a halogen and an alkane at the same time. So haloalkane. And then 2.2.2, the IUPAC name. Okay, so we already did it, right? It's 3,5 dibromooctane. So you can just copy it, and that's what you would do in a test, in an exam, right? So you already wrote it down for yourself, and yeah, now you can just copy it, and that's it. 3,5 dibromooctane, right? Yeah, so we're flowing. See, it's actually nice to look at this info before you begin. You flow. Okay, now it says consider compound F. Okay, we did have a look at it. It's a ketone, right? And then it says write down the IUPAC name of its positional isomer. Okay, so positional isomer, let's just look at it again. So if it's a positional isomer, it means this double bond to oxygen, it moves somewhere else, okay? So, well, for now, it's on the second carbon. I can move it to the third, okay? If I decide to move it to the fourth, do you realize it's the same as it being on the second? And if I move it to the first or the fifth, then it's not a ketone anymore. It's an aldehyde. So I can only move it to the third carbon, okay? And they are saying write the IUPAC name of its positional isomer. So instead of having it on the second, it's going to be on the third. Therefore, it is going to be pentan 3-one or 3-pentanone. Okay, and then 2.3.2, chain isomer. So now you won't just have a straight chain, okay? You can, change it up a bit, make it branched, okay? So I have 5 carbon atoms. So how about I make 4 of them, and in the second one, I have a methyl group, okay? I still keep the double bond to the second, so I have the first carbon, second, third, fourth, okay? So now what is this going to be? They want the name, okay? They don't want the structural formula. So now this is I almost said butane, but it's not. Now it's butanon, okay? But on the second carbon, I have, that's where it is, right? The ketone, it's on the second carbon. But I have a methyl group on the third carbon. So it will be 3-methyl and butan 2-one. Or I could have said 3-methyl 2-butanon. It's really up to you. So whether you placed, actually it wouldn't matter. Even if you took this methyl group on the second carbon and you put this ketone on the third carbon, it would still be the same. Yeah, it would still be the same. And you can't take the methyl to the end. Now it's still a straight chain, and you can't take the ketone to the end, it becomes an aldehyde. Now you have a functional isomer. You don't have a chain isomer anymore. So I hope through this you understand the difference between a chain isomer, a functional isomer, as well as a positional isomer. Okay, there is a difference. Okay, if they're in different functional groups, it's a functional isomer. If they are positioned differently, it's a positional isomer. If there are chains and the other ones are straight, that's a chain isomer. Okay. And then we go to 2.4.1. So during the reaction of compound A with compound E in the presence of an acid catalyst, two products are formed. So we have compound A, okay? We have a carboxylic acid. And compound E, it's an alcohol. So whenever you have a carboxylic acid and an alcohol, the product is an ester and water. Okay, so now, what are they saying? Okay, so that was just 2.4. All right, now we get to 2.4.1. Now they want the organic product formed. So they want the ester. So our carboxylic acid was methanoic acid. Okay, and then our alcohol, it was hexanol. Yes, E was hexanol. So if we put them together, what do we get? What will be the ethanol? What will be the O8? And so basically your carboxylic acid, okay, that part, it forms methanoate. Okay, but that's not it. The alcohol presents, or rather represents, so it'll be hexyl methanoate. So I don't know how you pronounce it, hexyl methanoate or hexyl methanoate, but basically your alcoholic part comes first. Okay, that sounded wrong. Alcoholic. The alcoholic section comes first, and then the carboxylic acid comes second. Okay, so now 2.4.2. Structural formula of its functional group. Okay, now we need to put down the structural formula. So I normally, when I actually put out the structural formula, I normally put the carboxylic acid first and then the alcohol. But because when we write down the ester, we start with the alcohol, I'll do that first. Okay, so I have 6 carbon atoms. Okay, and then I'm adding methanoic acid. So I have a double bond to the oxygen and OH and another H that side. Okay, so what forms part? So you take H2O out. Okay, and then when you finally draw your ester, it is going to be 1, 2, 3, 4, 5, 6, and you have your O, and you have a double bond, and then you have your hydrogen atoms surrounding your carbon atoms. Okay, and around oxygen you have your 2 bonds, and around carbon you have your 4 bonds, as it should be. All right, cool. So that is the structural formula. Okay, because they ask specifically for a structural formula, I would then put my hydrogen atoms in. Okay, let's just behave. Even though it's 1 mark, we gotta make sure we get every mark. Okay, and that is your hexyl methanoate. Now 2.5. Okay, this is a long question, my goodness. Okay, 2.5. So compound C, the decane, reacts at high temperatures and pressure to form a 3-carbon alkene and an alkane Q. So what happened there? So I have my decane, and it went into, so I have C10, H22, and it decomposed at high temperatures and pressures to an alkene, 3-carbon alkene. So I have 1, 2, 3. I'll just put the double bond there, alkene, which shows it's a double bond. Okay, and Q. So Q is an alkane, meaning we still have our alkane there with 7 carbons this time, because we already used up the 3. 1, 2, 3, 4, 5, 6, 7. And it's normal. So it's what? Heptane. Okay, so that is P and that is Q. Now, the type of reaction that takes place. Okay, so when you have the only reactions that can take place with an alkane is either substitution reaction or, yeah, either you substitute it or you break it apart. And that is what happens here. It's actually called cracking, okay? That process where you just break it apart. So in this case, you have cracking, okay? So yeah, that's what you can do to an alkane. You can either substitute the hydrogen atoms for maybe halogens, or you can take away, so eliminate. So elimination also happens with alkanes, and then it becomes either an alkene or alkyne, depending on how many hydrogen atoms you took out, or cracking, where it literally just breaks the structure apart, which is what we have right now. Okay, and now the molecular formula for compound Q. Okay, so molecular formula, you have 7 carbons remaining, and you have 14 plus 2, which is 16. So that is it. And yeah, guys, we're at the end. Okay, the structural formula for compound P, this is basically this. Okay, we're doing a copy and paste. Literally. So copy and paste. Okay, but now we need to put in our hydrogen atoms. Okay, so yes, hydrogen. I don't think they will penalize you whether you have your bonds shown like this, or if maybe you had it like that. I don't think they'll penalize you, but with me drawing those bonds like that, it's to show that realistically, that's how you would draw the structure. But yeah, and that is 2 marks. And I believe we are done with question 2. Again, I hope you enjoyed it. I did. This is actually nice. Yeah, so enjoy the rest of your day. And it is it from me. Hello everyone, and welcome back to MV Tutors. I'm Solo, and I'll be looking at question 3 with you guys today. Alright, so let us get to it. We're still on chemistry. Okay, we're done with physics. So yeah, chemistry 2021 June exam. Alright, so question 3. Learners use compounds A, B, and C to investigate one of the factors that influences the vapor pressure of organic compounds. So A, we have butane 1-ol. Okay, so but meaning 4 carbon atoms, and it's an alcohol. So it's alcohol placed on the first carbon. Okay, then B, we have butane 2-one. So it is a ketone. All right, again, still 4 carbons. And on the second carbon, that's where we have our double bond to oxygen. And then C, propanoic acid. So prop meaning 3 carbon atoms, and it's an acid, so we have a carboxylic acid. Okay, and then 3.1, they want us to define the term of vapor pressure, and it's 2 marks. Okay, so this is theory that you would know. Okay, and so what is vapor pressure? vapor pressure. Okay, that is the pressure exerted. Okay, pressure exerted by a vapor. Ooh, someone doesn't know how to spell. By a vapor at equilibrium with its liquid in a closed system. Okay, so it is the pressure exerted by a vapor at equilibrium with its liquid in a closed system. I think important thing here, you must say something about it being in a closed system and that vapor is at equilibrium with its liquid. Okay, so yeah. And then 3.2, so what does it say? Write down the independent variable for this investigation. Okay, independent variable. So let's say we have our graph there. We know that on the x-axis, this is our y-axis. On the x-axis, that's where you normally have your independent variable. Okay, so that's where you have your independent variable. Okay, because the y values, you get them from the x values. So y would be your dependent variable. Okay, now looking at this, so what are they trying to do? They're trying to investigate the factors that influences the vapor pressure. So your vapor pressure, we are expecting it to be on the y-axis. Okay, for you to get your vapor pressure, you need to know what functional group you're dealing with. We already have alcohol, we have a ketone, and we'll have carboxylic acid. Okay, so here we're expecting on the x-axis to have our functional group. Okay, because based on the functional group, you will then get to see how its behavior is. Okay, what is it? How the functional group actually influences the vapor pressure. So your vapor pressure is going to be on the y-axis, because you can't really get it without knowing what the functional group is. Okay, so ketones will behave this way, carboxylic acids another way, and so forth. And yeah, so basically, to answer the question, the independent variable in this investigation, it's actually the functional group. Okay, that is the answer. And then 3.3, which compound, A or B, has the higher vapor pressure? Okay, so how do we answer that? Okay, guys, when it depends on the intermolecular forces. We normally say IMF. Okay, so the higher your intermolecular force, okay, the strongest being hydrogen bonds, okay, and you have weak ones like dipole. Okay, so if your intermolecular force is very high, okay, it means that your boiling, or the boiling point, is also high. Okay, so the higher the intermolecular force, the higher the boiling point, and the higher the boiling point, it is inversely proportional to vapor pressure. So the lower your vapor pressure. Okay, so now we need to see alcohol versus ketone versus propanoic acid. Okay, so alcohol, guys, remember alcohol has the OH, okay, the hydroxyl, and this is hydrogen bonding. Okay, and then you have a ketone. Ketone, it's just carbon bonded, double bonded to an oxygen atom. Okay, so it has London forces. Okay, so it's not as strong as your hydrogen bonding. Okay, it's actually hydrogen bonding for your alcohols, but for your ketone, it would be London forces that are predominant there. Okay, you also do have London forces in your alcohol, but the predominant one is the hydrogen bonding, which is strong. So therefore, for A, basically, if I'm looking at your alcohol, which is A, and I'm looking at your ketone, which is B. A has higher intermolecular forces. Oh gosh. So it has higher intermolecular forces. Okay, and this one is lower. And as a result, it would have low vapor pressure ultimately, whereas B has higher vapor pressure. So to answer the question, which compound, A or B, has the higher vapor pressure, it will be B. Okay, so I'm gonna have to go charge my laptop later. Okay, I'm back. Yeah, so B will have the higher vapor pressure, okay, because it has lower intermolecular forces, resulting in lower boiling points. Therefore, your vapor pressure will be high. All right. Ooh, did I jump the gun? Because now 3.4 wants us to fully explain the answer to 3.3. Okay, guys, so when you answer these questions, you really have to refer firstly to the intermolecular forces. What type do you have for alcohol? What type of intermolecular forces do you have for butane 2-one, so 2-butanone, which is a ketone. All right, so we need to talk about the type of intermolecular force. So I'm just going to say I have my alcohol there. Okay, then I have my ketone. Okay, so firstly I want to comment on the intermolecular force type. So what type and intermolecular force strength. Okay, then I will comment on the boiling point. Okay, and ultimately the vapor pressure. Okay, so how does that all come together? Okay, are we cool? So for the alcohol, I did say that we do get some of the London forces, and then but the predominant one, okay, what makes it so, or rather for it to be stronger, the intermolecular forces between the atoms, for them to be tightly bound, it's because of the hydrogen bonding, which is quite strong. Okay, so yeah, let us comment. Okay, so like we said, for alcohol we have hydrogen bonding, the strong one. Okay, let me just do this. Hydrogen bonding. Okay, and then normally for your ketone, the intermolecular forces that you will find there are your London forces or your dipole forces. Okay, ooh, dipole force. Okay, dipole force. And the strength, so the intermolecular strength, it is quite high for the hydrogen bonding, whereas with the ketone, I mean, you can break up the molecule quite easier. Okay, easier than the hydrogen bonded molecules. Okay, so the strengths, for the alcohol it's quite high, for the ketone is quite low. As a result, the boiling point would be high for your alcohol, and for your ketone it would be low. And then ultimately your vapor pressure for the alcohol would be low, whereas for the ketone it would be high. Okay, so it's 4 marks. Yeah, I think I've mentioned 4 things to talk about. Yeah, I think so. So yeah, I don't know what to add. I don't. Okay, so let us go to 3.5. Okay. Alrighty, and now we're going to go to 3.5. So the graph below represents the relationship between vapor pressure and temperature for compound A being the alcohol. Alright, at sea level, okay, so yes, the pressure there, vapor pressure, you can see it's 101.3 kilopascals. That is the pressure that you'd expect at the sea level. Okay, X and Y represent different temperatures, okay? And then now they ask, write down the term for the temperature represented by X. Okay, guys, so at that point, 3.5.1, the temperature represented by X is actually the boiling point. Okay, so for your alcohol, at that pressure of 101.3, that's when alcohol actually starts boiling, or rather, not just any alcohol, but butanol. Okay, so that is the boiling point. Or boiling point, boiling temperature, but yeah, it is the boiling point. Okay, and then state the phase of compound A at temperature Y. Okay, choose from gas, solid, or liquid. Okay, guys, so before X, remember at X, that's where the boiling point is. So anything in front of X, okay, on the left of X, it's actually still a liquid, but on the right of X, it's a gas already. So at point Y, or rather temperature Y, it's already a gas at that point. Okay, so that's the phase there. Okay, and then let's just take it a bit up. Okay, so redraw the graph in your answer book. Okay, and on the same set of axes, sketch the curve that will be obtained for compound C. So you should label the curve A and C. Okay, so let's try drawing that or reproducing that graph. Okay, so there we have our y-axis and our x-axis. Okay, and there we have A looking something like that. Okay, and so that's A, and then what else do I need? So we have 101.3. This is our vapor pressure, kilopascal. Okay, and then we have temperature, okay, in degrees Celsius. All right, and then we have our dotted line. Okay, that is where X is, and we have Y, something like that. Oh no. Okay, I see my error. I'm gonna fix it right now. Okay, so that is where 101.3 is. That is X, and we have Y somewhere there. Okay, I don't know why this did that, but I'm gonna say that is A. Now we need to draw the graph for C. And C, if you remembered, that's the carboxylic acid. Okay, so now I'm gonna have to sketch it. So what do we know, guys? Okay, so carboxylic acid, it also has hydrogen bonding there. Remember, it's Cu, where one carbon is double bonded to oxygen, and on the same carbon is also bonded to a hydroxyl group. So carboxylic acid, its intermolecular force is stronger than your alcohol. Okay, and remember we said the higher the intermolecular force, the lower the vapor pressure is. So if the vapor pressure of A is what? At temperature X, it is 101.3, then we are expecting, at this point here, at 0, okay, so the vapor pressure, it's what, less than 101.3 for A. We are expecting C to be lower. Remember, it has a lower vapor pressure, but it has a higher boiling point. So if for A, it boils at X, okay, maybe for C, it would boil at Y. Okay, so this point would shift that way to Y. I'm just saying. Okay, but the boiling point has to be higher than X for the propanoic acid. Okay, yes, it does count that there are 3 carbons for propanoic acid as opposed to butanol, which is 4 carbon atoms. So you won't get such a huge difference, but for illustrative purposes, I'm gonna use that distance in between. All right, but still, even though propanoic acid only has 3 carbon atoms, it still has a higher intermolecular force than the alcohol and a lower vapor pressure. Okay, so you would have something. Let's see if we can draw it all nice. Yeah, we tried. Okay, and that is C. Okay, and that is it, guys. Yeah, 2 marks. Actually, question 3 was quite short, but I hope you learned something. And please, guys, if you do need a session, do contact us. Visit our website on www.mvtutors.co.za. See you next time. Hello everyone, and welcome to MV Tutors. I'm Tilo, and I'll be looking at question 4 with you guys. Yeah, question 4 is the last question on organic chemistry, and it has to do with organic reactions. Okay, so let's have a look at what we have and let's answer the questions. Okay, so the flow diagram below shows the conversion of propane to propan-2-ol. Okay, so we have propane and it goes through various steps to get to propanol or 2-propanol. Okay, alkane being saturated, the different kinds of reactions it will go through, either elimination, substitution. Okay, you can't add to it because it is saturated. Alkanes are normally, the reactions they go through, they're quite slow. Okay, and for it to be quickened, if you want to speed up the reaction, if I could say, you would add heat to it, okay, or sunlight or UV rays or whatever. So they're quite slow and they need help to to get right along, to move along. Okay, so you have your alkane here, which is propane, and I actually just want to draw out what is happening. Like I said, I like drawing out the structures. It helps me answer the questions much quicker. Okay, you can do it however best works for you. Okay, so I have propane. Okay, so 3 carbon atoms with their respective hydrogen atoms surrounding them. Okay, and then in step 1, I'm actually adding bromine. Okay, bromine is in group 7. For it to complete the octet rule, it needs to come in pairs. Okay, so it doesn't come alone. It's not just Br, it's actually Br2. Okay, and if you have an alkane and you add a halogen to it, okay, so the result will be a haloalkane. Okay, so basically this is a substitution reaction. So basically we have our 3 carbon atoms. One of the bromine atoms is gonna come on here. Okay, but now the question is, on which carbon will it go? 1 or 3, that's pretty much the same. If it goes to carbon 1 or 3, they're both at the end, so it doesn't matter. But the question is it really on 1 or 2? Okay. What will guide you guys is the alcohol formed at the end. Do you see it is propan-2-ol? So it's on the 2nd carbon that you have your bromine atom. Okay, while the rest are just your normal H or hydrogen atoms. Okay, so basically, yeah, you have your propane plus a halogen, and this whole reaction here, we call it halogenation, and it is a substitution reaction because we are substituting one hydrogen atom for one bromine atom. Okay, and then what happened to the other bromine atom? Basically, we have your H and bromine there. So if it was HCl, we would have called it hydrochloric acid. So I don't know, can we say bromic acid? But it's hydrogen bromide, let's be safe there. Hydrogen bromide that forms. And guys, the interesting thing is, this is your organic compound, okay? This part here is organic, this is inorganic. Inorganic, okay? And what else can I say? Oh, like I said, if you're gonna have reactions with alkanes, they are really slow. You need to add some heat to it, okay? Heat, sunlight, UV rays, whatever. You need heat to just speed things up. So basically, we've just highlighted what happens in step 1, okay? So step 1, there it is. And X, okay, X that forms, because we are dealing with organic chemistry, we're not going to concern ourselves much with the inorganic compound, hydrogen bromide. We're going to literally just focus on the organic compound. So this is your X. Okay, now we undergo step 2. So there you have your structure there. Okay, so bromine and all your hydrogen atoms. Okay, we didn't name it previously, but we can name it now. It'll be 2-bromopropane. Okay, because it is a haloalkane. All right, cool. Now how do we go from 2-bromopropane to propanol? Okay, so it can undergo a reaction of hydrolysis. Okay, you can either go through hydrolysis. Okay, it will undergo hydrolysis. For you to get alcohol, it will have to undergo hydrolysis. But you can either have water there, or you could have, from your group 1, let me just show you on the periodic table. From group 1, we have sodium, lithium, potassium. Yeah, so lithium, sodium, potassium. So if you guys have the study guide, Mind the Gap, you would know they would recommend you use sodium hydroxide. So it could be sodium hydroxide or lithium hydroxide or potassium hydroxide. Okay, but I would prefer sodium hydroxide in this case because I've seen it being used often. So you could either go with water or sodium hydroxide. But what does that do? Okay, what would be the solution there? Again, you have an alkane. Okay, an alkane either undergoes elimination or substitution. Okay, so in this case, we are ending up with propanol. Okay, we still have 3 carbon atoms and 8 atoms surrounding it. Okay, so okay, we have OH and 7 atoms, hydrogen atoms surrounding it. So we're definitely not gonna go through elimination. We're still gonna go through substitution. It's still a substitution reaction. So substitution reaction, and the type is hydrolysis. Okay, what did I do? The type is hydrolysis. So what will happen? You're substituting your bromine atom with what? With hydroxide. Okay, so whether you get the hydroxide from water or from the sodium hydroxide, you will use hydroxide. Okay, so there you have your 3 carbon atoms. And as the answer suggests, on the second carbon, that's where you have your hydroxide. Okay, and the rest will just be your normal hydrogen atoms. And then what is left behind? Okay, if you had water there, what would be left behind would have been, let me just do this. What would have left behind would have been hydrogen bromide, because you would have taken the hydroxide out. But if you go with sodium hydroxide, what is left is sodium bromine. And in this case, because like I said, in study guides and textbooks, they normally go with the sodium hydroxide, okay, when you do the hydrolysis. Okay, so yeah, at the end, you end up having your propan 2-ol or 2-propanol. Okay, so we have done step 1, which was the substitution called halogenation. Then we have X, which is there, all right, and then step 2, again substitution but undergoing hydrolysis, and then our final answer, which is propan 2-ol. And your hydrogen bromide or your sodium bromide is the inorganic compound that forms. So now let us answer the questions. We should be flowing. We should be flowing. So now it says state one reaction condition for step 1. Okay, guys, alkanes, I'll say this again, they are slow. So you need something to quicken the process, and you would apply heat to it. Okay, so you need heat. Whether it is heat or light, something, sunlight, yeah, you just need heat, basically. Okay, and then 4.1.2, write down the name or formula of the inorganic compound formed in step 1. We talked about it. The inorganic compound is hydrogen bromide. Okay, they said the name or the formula. So hydrogen bromide, I would stick to that, the formula. And then 4.1.3, name the type of substitution reaction represented by step 2. It is hydrolysis. Okay, and then 4.1.4, write down the name or formula of the inorganic reagent needed in step 2. Not the inorganic reagent formed. The one that formed is sodium bromide, but the one that's needed is sodium hydroxide. Okay. And then 4.1.5, write down the IUPAC name for compound X. So X, did we talk about? Yes, we did. We actually did name it. It's 2-bromopropane. Okay, I'm not going to rewrite that. I'm just going to copy and paste. Okay, so there we go. 2-bromopropane. Okay, yay. And then let me just do this now. My answers look somehow. Okay. And then yeah, that's it. That is what? 6 marks for all of that. Now we get to 4.2. Okay, and then ethane can be prepared from chloroethane by a 2-step process. You are supplied with the following chemicals. Now select chemicals in the table above that can be used for this preparation. Now using the condensed structural formulae, write down a balanced equation for each reaction. Indicate the reaction conditions for each reaction. So basically, if there are catalysts that are required, you will have to put it there. Like what we did there, we applied heat. Even here, we can actually indicate it with like a triangle there. Okay, so heat. You can say that. So let us see. We have ethane, and we want to go to ethane. Okay, so chloroethane, basically ethane, you have 2 carbon atoms. I'm just going to put the structural formula here, and it doesn't matter where you put the chlorine, it's pretty much the same, because yeah, it's just 2 carbons. So you have that. You want to get rid of that chlorine, guys. And you want to put in hydrogen. And please do not be tempted by saying you're going to do substitution reaction and then you put H2 there. No. Okay. But yes. So we have a haloalkane. Okay. Haloalkane. And guys, with this haloalkane, I do wanna get rid of this chlorine atom. Okay, so what do I have to do to get rid of the chlorine atom? Well, basically, you have addition, and then now we're gonna do elimination. Okay, so we want to eliminate. All right, and in eliminating, I have a halogen. Okay, and it doesn't go by itself. Guys, chlorine doesn't go by itself. Either it'll be Cl2 or it'll be HCl. We need to respect the octet rule. So if I'm going to eliminate, I can't just eliminate chlorine by itself. I would have to eliminate it with another hydrogen. Okay, so it'll undergo elimination reaction. Okay, and what will that type of elimination reaction be? It'll actually be because I'm going to get rid of a hydrogen and I'm going to get rid of a halogen. So that will be dehydrohalogenation. Okay. Whew. Yeah, dehydrohalogenation. What a long word. And what do we have? If we're going to eliminate them, okay, guys, then I'm going to now form a double bond. Okay. And I have my hydrogen atoms there. Okay. So we have eliminated it. Now we need to look at our table. Yeah, for you to eliminate, what would you have to use in this table? Okay. Okay, so again, like I said, whenever you have an alkane, it needs heat, right? You always need heat to get things up, to get things working, all right? So, okay, guys, they actually mentioned here, use condensed structural formulae. So I just wanted to put the structure there, but let's write it properly. What actually happens? So I have my carbon. Okay, I'm going to say this is 1. Carbon 1 and this carbon 2. So I have my carbon CH3 and then CH2Cl. Okay, and then what will actually, apart from heat, what will help me with this elimination reaction? It's actually if I use diluted or concentrated. They actually gave us concentrated. So if I use concentrated sodium hydroxide, okay, and then under heat we then have our alkene there, okay, so CH2CH2, and then what happened? Okay, so basically I had my chlorine and my hydrogen that I removed, okay. So chlorine has a negative ion, it has a negative charge, okay. Hydrogen has a positive charge, and there I added sodium hydroxide, okay. Sodium with a positive charge and hydroxide with the negative charge. So all of those in solution, which one will go to which? Okay, so you're gonna have your they're actually next to each other. You're gonna have your hydrogen coming together with your hydroxide and it forms water. Then you're gonna have your sodium coming together with your chlorine and it forms a salt. All right, so your products, you're gonna have your alkene, okay, then you're gonna have your sodium chloride, then you're gonna have water. Ooh, I'm squeezing everything in there. But yeah, basically you're gonna have that, okay. And is everything balanced? Yes, I have one sodium atom, one chlorine atom, two carbon atoms, and this side I have 6 hydrogen atoms. On the right I also have 2, 4, 6, and one oxygen atom, so it is balanced. So using condensed structural formulae, write down a balanced equation for each reaction. So for reaction 1 we are done. Okay, we've managed to get our alkene through the elimination reaction called dehydrohalogenation. Okay, we removed a hydrogen and a halogen, and it all reacted. Sodium chloride in aqueous solution, water, liquid, and yeah. Now we're gonna take our second reaction. We're gonna take that. I'm gonna draw a structural formula now. So now we have our double bond alkene. Okay, I am trying to get to an alkane, okay, which is ethane. This is what I'm trying to get to. So what will I do to have this? I'm going to have to add hydrogen, okay? And again, hydrogen doesn't come alone. It comes in pairs. It's a diatomic molecule, okay? So I have, yeah. And then the catalyst required there to break this double bond to a single bond, that catalyst is actually platinum. Okay, and yeah, so what do I, yeah, I think that is it, guys. So we're definitely using H2 there. Yeah, that is it. We don't need anything that's concentrated. Yeah, those are the chemicals that I need. So if I were to write this down as a condensed structural formula, I have CH2, just take it up, and CH2 plus H2. Remember, it undergoes an addition reaction, and that kind of addition reaction is actually called hydrogenation. Just shift this a bit to the bottom. Okay, it's actually called hydrogenation because you are adding hydrogen. So hydrogenation. Okay, so yeah, we have CH2, CH2 plus H2, and then ultimately we have CH3, CH3, which is what they wanted, and it's a two-step process. Yeah, let's not forget that platinum over there. And yeah, I think that is it, guys. I don't know if I've missed anything, but we have used our concentrated sodium hydroxide, we have used platinum, we have used hydrogen, and we now have successfully prepared ethane from chloroethane. And we have also indicated the reaction conditions. I think we're done. All right. So I hope you've learned something. If you have questions, comments, anything really, just please comment down below. Otherwise, you can visit our website for more videos, for more content. If you want to book a lesson, you can do that as well on www.mvtutors.co.za. And that's it, guys. Enjoy your day.
Well, hello once again. Welcome to MV Tutors. I am Figa Manana. So I'm gonna do question 5 right now. This is the June 2021. Let me just show it. June 2021 exam. Paper 2 and question 5. Okay, you just wrote this just a few weeks ago, so let's do the memo right now, and let's try to explain it in a more digestible way, or rather, physics, chemistry made simple. Anyway, let's get right into it. It says here, 2 experiments, 1 and 2, are conducted to investigate one of the factors that affects the rate of reaction of aluminum carbonate with excess hydrochloric acid. The balanced equation for the reaction is, now whenever they give you an equation, number one, you need to make sure it's balanced. And number two, having made sure it's balanced, just check the numbers that are balanced, because these are the ratios you'll probably need in the question. And then it says the apparatus used as shown below, hydrochloric acid, they put it on top there, and then there's the aluminum carbonate over there. And then they said the reaction condition used for each experiment are as follows. Experiment 1, it's 100 centimeter cubed of this concentration of hydrochloric acid reacts with 0.016 mole of aluminum carbonate granules at 25 degrees. Now, that's experiment 1. Now, let's see how different experiment 2 is. Okay, so experiment 2 is half the volume. As you can see, with experiment 1 was 100, but 2 is 50. And then let's check out, the concentration is more, so we've got more concentration of acid. Okay, the number of moles are exactly the same, the temperature is exactly the same, so the only change here is really just the volume and the concentration. Take note of that, might need it in the question. So question 1 then says define the term rate of reaction. Okay, let's define it. So rate of reaction, therefore, the rate of reaction is simply the change. Now, it's a change of many things. Okay, it can be a change of concentration. Okay, rate of reaction depending on the experiment you're doing, or it can be the change of number of moles. Could be that number of moles, measurable. Could also be the change in, let's say, volume. Okay, also it could be a change in mass. Okay, but all of these changes, okay, they are per unit time. Okay, so per unit time, it means it could be per second, it could be per minute, per hour, whatever parameter has been chosen in that experiment, but it's the change in all these variables: number of moles, volume, mass, concentration, all of these things. Okay, simply. And then 5.2 says, using the experimental setup above, states the measurements that must be made to determine the rate of this reaction. Now, we have written that actually the rate of reaction is a change in one of these things. Okay, so if we look here, what do we have? In this experiment, we definitely have been given volume, so we can change volume, we can choose it. So as our answer, we can say this is now 5.2. So for 5.2, we can now say we can change the volume. And remember, we said it's per unit time, so volume and time. Those are the two variables that we can do over this experiment. Okay, so we can monitor the change in volume. Okay, but in all honesty, it could be any of these: concentration and time, number of moles and time, mass and time if you can, but I think the more accurate one is volume. Okay, because we've been given the volume, and time is just, it has to be there. Okay, so now it says use the collision theory to explain how the average reaction rate in experiment 1 differs from the average reaction rate in experiment 2. So we can pick one. Okay, let's just continue with volume, but no, let's pick something else. Let's pick, what do we have? Concentration. Remember we said here the difference is volume and concentration. So what can we say about concentration? Concentration of hydrochloric acid is more. Okay, so this is now, let me write it this side. I want to write it this side. So what we have here in 5.3 is that what we can say is that the concentration, number one, we have concentration is higher. Concentration higher. So the concentration is high, which means we increased concentration. And what happens when you increase concentrations? You have more collisions, which lead to more effective collisions. Okay, I just want to say more effective collisions, because it's all about effective collisions. If you don't understand what effective collisions is, just view one of my previous lesson videos I've done on rates of reaction. I explain it very well there. So effective collisions. The collision theory is all about effective collisions. So the more effective collisions there are, the higher, therefore, higher rate of reaction or reaction rate. Okay, so that's just it. That's Le Chatelet, not Le Chatelet, sorry, the collision theory. Okay, it's all about effective collisions, and the more effective collisions you have, the higher the reaction rate is. Okay, now let's go to the next question, 5.4. The average rate of reaction in experiment 2. So we're on experiment 2. During the first 2.5 minutes is that. Calculate the number of moles, okay, of that remains in the flask after 2.5 minutes. Okay, so check this out. Remember we defined rate of reactions, and in the definition there we did mention that we could also use the number of moles per unit time. So that's exactly what we're gonna do here, because what you want to do in each question, you want to pick the information that you've been given, use that information to answer the questions. So here we go. We're gonna say 5.4. we're gonna say, okay, so the average rate, let's just say average rate of reaction, okay, is equals to the change in number of moles per unit time. So that's a change in time as well. So under average rate, that's where we can put this which we have been given. Okay, it's 4.4 times 10 to the power minus 3, which is equals to change in number of moles divided by the change in a time. Okay, all right. Oh, the change in time we've been given actually, so I don't need to write it like that. I can just put it as 2.5 minutes. Okay, and then now to complete number of moles of that. Okay, so this is the average rate. Okay, I'll explain it as we go, how that affects the rest of the experiment. So times 2.5 is equals to the change in number of moles. All right, so let's just quickly put this in a calculator. So I'm just going to grab one here, and I'm going to say 4.4 times 10 down here to the power negative 3, and I'm going to say that's times 2.5. Okay, so that's 0.011. All right, so 0.011 is the change in number of moles. Now, pay attention to what's happening here. They want us to solve the number of moles that remain in the flask for these metals here. Okay, these carbonate metals here, aluminum carbonate. Okay, and we have been told in the question that actually they start initially with this number of moles. So if they start with that number of moles and the change of moles is that means to get then the final answer of number of moles, we have to say the initial number of moles minus the change in the number of moles. So the initial is 0.016 minus then the change, which is 0.011. Okay, so if I put this in a calculator, I'm gonna get, I won't put it because I can just see it from here, 16 minus 11 is 5, so it's gonna be 0.005 moles, just like that. That's our final answer right there. Okay, good. We're done with this question. Let's move to the next one. It says now calculate the maximum volume of carbon dioxide that can be prepared at 25 degrees Celsius in experiment 1. Take molar mass volume at 25 degrees Celsius as 24,000. Okay, so what we want to do here then, 5.5. First of all, let's see what information we have on experiment 1. We have that experiment 1, we have this number of moles of aluminum carbonate, and what we are looking for, okay, so we have this number of moles. What we calculate the maximum volume of carbon dioxide. Okay, so what we are looking for is carbon dioxide. So if we have that, which is 1 mole, and carbon dioxide is 3 moles. So what that means is that I'm just going to say, okay, first of all, when it comes to number of moles of that aluminum carbonate, just gonna write it there, versus carbon dioxide. I know based on the balance equation it's 1:3, and I know that the actual number of moles then is 0.016, which means to get this one I have to say 3 times 0.016. and that's gonna, let me just grab a quick calculator here. Okay, so let's say 3 times 0 0.016. It's gonna give me 0 0.048. So it's 0 0.048. This is the number of moles of carbon dioxide. Okay, so what am I gonna do with this information right here? Mole, this information right here. Now, if you actually go to the formula sheet, you will see that when it comes to gas volume and the number of mole equation, you will have that the volume divided by the molar gas Vm, it will give you the number of moles. So here we have solved the number of moles, so we're gonna put 0 0.048 this side, which is equals to the volume we are looking for divided by the molar gas volume, which is 24,000. Okay, and therefore to solve our final volume, then we're just simply gonna say 0 0.048 times 24,000. Okay, let's bring back our calculator as we're going to need it right now. So it was 0, I didn't have to delete that, I really didn't, times 24,000. There we go. That gives us 1152. And what's this volume in? You need to be careful of your units, because here we have this in moles, but we have in centimeters. Let me just write it for you. This is in mole, and then this 24,000 is in centimeter cubed per mole. Okay, so what happens? The moles cancel each other and you are left with centimeter cubed, and that is our final answer. Well, I hope you understood that, but in the event that you didn't, please do contact us. Don't stay confused. All right, well, that's it from me. See you next time. Well, hello there. I trust you're having a good day. My name is Figa Manana, and I am from MV Tutors. Well, I am here to serve you today with question number 6. All right, so let's get right into it. Oh, before we get into it, just a disclaimer that if you need a tutorial session after this, go ahead, contact us. Visit our website or drop a comment down under here. Otherwise, just keep watching our videos. All right, now it says here, question number 6. This is from the June 2021 past exam. It's not really past because it's not that much past, because you just wrote this a few weeks ago. Okay, and at the time of this recording, it's been like, I don't know, 5 weeks since you wrote this exact exam. Okay, but we're doing paper 2 now. Question number 6. It says pure hydrogen iodide gas HI of concentration 1 mole per decimeter cube is sealed in a 500 centimeter cube Now, you must pay attention to these units because concentration is given in decimeter cube, but the volume is given in centimeter cube. So when it comes to question time, we need to convert, probably we'll need to convert the centimeter to decimeter. We'll see. At a temperature T, the reaction reaches equilibrium according to the following balanced equation there. That's very important to tell us that the equation is balanced already. That's what we want to hear. That's what we want to use. Now it says define the term chemical equilibrium. Okay, now chemical equilibrium, if you look at, take a look at this sign right there. That is what is talking about chemical equilibrium. And so then chemical equilibrium is actually when the forward rate, or when the rate of reaction of the forward when the rate of reaction of the forward reaction is equal to that of the reverse reaction, is equal to that of the reverse reaction. Okay, so when the forward is equals to the reverse, that is when we say the reaction has reached chemical equilibrium. Okay, now it says the graph below shows how the concentration of the reactant and products vary with time during the reaction. Okay, now let's just scroll a bit down to see what else can we get. What's the question? Okay, we see we've got X and we've got Y. Now, if you know your theory, you will know that when it comes to concentration, we start with reactants being highly concentrated. So they start high. So Y is probably, it's most probably the reactants, and then the products, they start at 0 because they haven't been made yet. And the more the reaction happens, the more the products happen. So that's the graph of X. Okay, so we've identified it before we even need to read the question. Okay, so every time you read a question, make sure you pick up these clues as you read the statement, so that by the time you go into the actual question, you already have some sort of stance to stand on. Now, 6.2.1 says, which one of the curves X and Y, wow, they actually asked us, represents the changes in the concentration of the product? Give a reason. Well, now because we discussed it earlier, we can confidently say, okay, let me just put it here, 6.2.1. We can confidently say which one of the curves X or Y represents changes in concentration of products. Okay, so product, you can safely say they're represented by X. Give a reason for your answer. The reason is actually because there are no products initially. No products as a general rule initially. Okay, so you start off having 0 products because all you have is just the reactant. Okay, so that's it. Let's go to the next question. How does the rate of the forward reaction compare to that of the reverse reaction at time t, time t 4 minutes? Choose from higher than, lower than, or equal to. Okay, so we are talking about the rate of the forward reaction versus the rate of the reverse reaction. At time 4, at T4, they have not reached equilibrium yet. Okay, they have not reached equilibrium yet, which means if you look at the graph of basically you check which one is steeper. It looks like the one for the forward reaction is the one that is steeper than the one for the reverse reaction. Therefore, based on that, we are going to choose higher than. Okay, do not say equal because they are not equal. All right, this might be a meeting point where they cross each other, but they are not equal. They only reach equilibrium at T6 because that's when they are both flat. Here, they are still reacting and not at the same rate. In fact, because this one, the Y1 is steeper, and that represents the forward reaction, okay, then we can say that it is higher than. They didn't ask us for a reason, so we're just gonna put higher than. But if they ask for a reason, we would say because the graph is steeper for the forward reaction. Cool. Now 6.3 says the equilibrium constant Kc for the reaction is 0.04 at temperature T. Where is that? T. Okay. Calculate the number of moles of iodine present at time 6 minutes. Okay, so now they've reached equilibrium, and this is an equilibrium constant Kc. All right, so we can work with that. Okay, so first of all, if you have watched, you should go watch my videos on chemical equilibrium, because there I teach a method which I call the Rice method. Okay, I prefer calling it the Rice method, and then I normally add an extra e, Rice E method. Okay, so what does Rice stand for? Okay, let's do this. Actually, let me just draw a table out. I'm gonna need a grid paper, so there we go. We've got our grid paper, and then what I want to do is I want to, on my grid paper, I'm gonna write Rice. I'll write it over there, but here what I want to write is the reactants, which is just HI. I want to write the products, which is H2. Okay, and then I want to write the other products, I2. Okay, where did I get this from? I got it from the equation, the actual equation that we give in this one. 2H2, 2H1 is equals to H2 plus I2. Now, you need to be careful. You can only do this if, only include if they're on a gas state. If one of them was in a solid state, we wouldn't include them here. And then what I want to do next then is actually write the rice on the side. Okay, so rice, the R stands for ratio. Okay, and it's in mole. All right, the I stands for initial. Initial. It's also in mole. Okay, we're talking moles here. The C stands for change. Okay, let's just say mole. It's also in mole. And then the E stands for equilibrium. Okay, so I'll just write equi. It's also in mole. All right, and then the last E is also equilibrium. But now the difference is this one is in mole per what? Decimeter cubed. You guessed it right. Okay, I just want to draw the table now just to complete it. So I'll draw. Oh, that's too thick. No, it's too thick. Let's go with that one. Okay, there we go. There we go. Now separating the reactants and the products, I like to put a double line so that you can tell that these two are separate. Okay, let me give myself some space. All right, let's get back there. Draw that line. There we go. This is to complete our table. Okay, let me just put these ones too, just for control, so that we are able to properly separate, because I'm not sure if you can see the blue lines. I wouldn't want to assume you do, but I'm pretty sure that you do, but I don't want to leave it to chance, so I'm just gonna draw out this table and complete it like that. Okay, there we go. Let's go back to our question now. What we need to do is start filling in this question. Let's start with the ratios, because we have been given the ratios. So the ratios are 2 for HI, 1 and 1 for the products. So we're just gonna put those numbers here. We're gonna put let's use red this time. We're gonna put, okay, I want it a bit thick. We're gonna put 2, 1 and 1 over there. And then initially, the number of moles that you always initially start with when it comes to products is you always start with 0 and 0. Okay, but for the reactants, those ones you start with something. So let's see, can we calculate it? All right, we have been given here a concentration and a volume, so we need to get rid of them, so that we need to use them so that we just get the mole. All right, so we know that by definition, a number of moles is equals to C times V. You can just check that formula out from your formula sheet. It's going to be there. Okay, so the concentration is 1 mole per decimeter cubed times a volume of 500, okay, centimeter cubed. But to convert it to decimeter cubed, then that's where we need to divide by 10,000. Okay, all right, I need to put this in a calculator, so let me just grab one right there. So we have 500, not 1,000, 500 divided by 10,000. like that. 1/20, give me decimal, 0.05. Gosh, did I do that right? 0.5. Hold on, didn't I get 0.05? My calculation, it's not right. No, I should divide 500 divided by 1,000. Yeah, that's it, 0.5. There's no, because now I when I did this question initially, I know that I got 0.5. It wasn't 0.05. Okay, so 0.5, which means we divide by 1,000 to convert to centimeter, to decimeter. We divide by 1,000 so that we get 0.5. From there, this is in moles. Okay, so we're going to put 0.5 over there. All right. Okay, so what else do we have in this question? We have nothing. That's all we've been given. So always, regardless of the question, you always start with what you have been given. And then I can go back and read the question. What do they actually want? Okay. They say the equilibrium constant Kc for the reaction is 0.04 at temperature T. Calculate the number of moles of iodine present at time T6. Okay, time T6, that's when it's in equilibrium. That's all we need to know. We're not going to use that actual time. So what they want here is the number of moles at, actually it's not there, at equilibrium. Okay, so the number of moles of iodine at equilibrium. Okay, so we know the number of moles of iodine will be represented by X. Okay, now they are also going to be equals to this. Okay, before I get there, let me just let's deal with the ratios. Now I want you to know that there is a relationship between, actually let me do it this way, between the ratio and the change. Okay, that's where the relationship counts. Okay, so if I have 1 mole of iodine, then I'm going to have 2 moles of HI, and likewise one mole of this. So I can go ahead and fill this in because it's 1:1. Now this as well, the change is 1 there and 1. Now the way we do this is that when it comes to the products, you always add the initial plus the change. It gives you the equilibrium. But when it comes to the reactants, you subtract. It's the initial, you subtract the change. Okay, so but first, what is the change that we need to fill in here? And you can see the relationship between the ratio and the change is 2. So it's just gonna be 2x, because 1:2 is the ratio. So remember, at equilibrium, I said it's 0.5 minus 2x. Okay, now when it comes to this equilibrium, the only difference is that it's divided by volume. Okay, and remember our volume is 500 divided by 1,000, which is 0.5. So what this means is that, first of all, let's start with iodine. It's X divided by 0.5. This side as well, that's the concentration, 0.5. This side as well is 0.5 minus 2x divided by 0.5. That's it. Okay, so we filled our entire table. Again, how does this help us now? Now we can go into the equilibrium constant, Kc, and they said it's 0.04, I think. Yep. They told us that Kc is actually 0.04. What can we do with this information? We know that the formula for Kc is actually equals to the products concentration, which is the H2 concentration, and the iodine one. Okay, and that's going to be divided by the concentration of the reactant. Now remember, its number of moles is 2, so we put it up there. Okay, and then moving forward from there, let's just start filling in what we have. We know Kc is 0.04. That's equals to the concentration of H is just X over 0.5. Concentration of iodine as well is just H 0.5 divided by Hi, concentration of Hi. There it is. It's 0.5 minus 2x divided by 0.5. Just like that. Okay. Cool. Now, ladies and gentlemen, all we have to do is mathematical gymnastics. I love that. Mathematic gymnastics. Just remember this is squared, right? So what we'll do to try simplify this, we'll just say 0.04. And then I'll just bring the whole thing. I'll bring in the denominator, cross multiply it. So I'll bring it here. And then we're gonna have, and then I'm also gonna just simplify it. 0.5 divided by 0.5 is 1, minus 2 divided by 0.5 is 4. Okay, and then x, and then this is squared, and that's equals to x times x is x squared divided by 0.5 times 0.5, that gives us 0.25. Okay, all right, let's continue with our gymnastics. So we're gonna say now we're gonna get rid of this fraction as well by multiplying 0.4 by 0.25. Let me just bring up my calculator real quick because I don't know that one by head. 0.04 times 0.25, we get 0.01. Okay, thank you. So I get 0.01, and then I need to multiply this out. Now I know this is simple what I'm about to do, but I find that it saves a lot of you from trouble. So do it. Just because it's squared, open both of them. I know you can do it in one move, but sometimes it's better just to keep things simple. Remember, we've already used this 0.25 here. So what I'm gonna do is just cancel it and put the x squared, excuse me, need to put this slide back. Stick, okay? Okay. Be a good boy. There we go. Okay, I need you to be a good boy. Behave light. Right, now I'm just gonna multiply them in. Okay, I'm just gonna do this. These are the gymnastics that multiplies that. I also always do this exercise because under the exam pressure, it's easy to make a mistake and miss some things. Okay, so I have 1 times 1, it's 1. Just follow the lines on top, and then the next one is 1 times minus 4x, which is minus 4x. The next one is minus 4x times 1, which is minus 4x. Minus 4x times minus 4x is plus 16x squared. Close the bracket. I just want to bring this x to this side so that I have everything in one side. Okay, now all that's left for me to do is just simplify. Let me just simplify the what's inside real quick. The one is on its own. Minus 4x minus 4x is minus 8x plus 16x squared. All right, minus x squared is equals to 0. I don't know what's going on with this slide. It's just misbehaving. Technology sometimes fails us and we find ourselves at a loss. Okay, behave light, please. I'm in a session here. All right, so I just want to multiply this in so that I get rid of the numbers. Okay, so I'll do this exercise. It needs to multiply in there, and in there. So 0.01 times 1 is just 0.01. Oof, I need a calculator for that one. Come back, calculator. So we're gonna have 0.01 times 8, and that's gonna give me 0.08. Okay, let me just do it for 16 while I'm here. 16, 0.16. Okay, so this one was 0.08x plus 0.16x squared minus x squared. That one is equals to 0. Now I can start putting things together. Okay, so what I'm gonna do then is put these two together because they're x squared. So it's just minus 1 times, plus, I need a calculator. All right, so it's negative 1 plus 0.16, and I get negative 0.84. Okay, so I've got negative 0.84 x squared minus 0.08 x plus 1 plus 0.01. I just put them in order. Okay, now I need to solve for x. Every time I solve for x, the safest route, just like doing these lines, is using the quadratic equation, which says x is equals to minus b plus or minus the square root of b squared minus 4ac. Okay, and that's gonna be divided by 2a. All right, we need to identify which one is a. A. I always do this exercise as well. That's B, and that's C. Okay, so I can now substitute. Let's give ourselves some space. Substitute back. So it's gonna be minus B is actually minus 0.08, plus or minus square root of B squared. B is minus 0.08, even though it doesn't really matter that much when it comes to squared numbers. There's still gonna be a positive value. Minus 4. A is minus 0.84, right? And then C is a positive 0.01. Cool. So all of this is under a square root, and all of it, let's just do, all of it is divided by 2 times A. A is minus 0.84. Okay, cool. Let's get a calculator real quick. Okay, there we go. So first of all, open your calculator like that and put in your, what do you call this, fraction, and then put a negative, put it exactly as it is, and then put a negative again, 0.08, close it. We'll start with a plus, and then put the square root, and then yeah, do it exactly like how we wrote it here, negative 0.08, and square that, minus 4, open the brackets, there's a negative 0.84, close it, open another one, 0.01, close it. Then you can come downstairs and then put 2, open a bracket, put a negative 0.84 and close that. Let's see what that gives us. It's a nice number. It gives us a negative 0.16. So x is equals to negative 0.16. Can't use that, so let's go back to our calculator. What we're going to do now is going to change that sign into what did I just do? Don't tell me I gotta start this thing all over again. There it is. But why is it doing this? It's not what I want. I want this equation, because what I want to do is actually change that positive into a negative, subtracting it now. There we go. 0.071, and it's positive. Okay, so x is equals to 0.071. Okay, it's either or of this of these questions. Now, can we ever get a negative solution? No. So this is not a correct answer. This cannot be equal. So the correct answer is therefore that one. And then what were we solving again, just to remind ourselves? The number of moles of iodine. Okay, number of moles of iodine. So that means our thing is gonna be, our answer is gonna be in moles. Okay, that's our final answer right there. Now that's it for this question, but the exam actually continued to this one over here. Now here they say the graph 6.4, the graph Below shows how the rates of the forward and reverse reactions change with time. Okay, there we can see the forward one is the solid line, the reverse, the dotted line. Okay, the temperature of the container is increased at time t10, 10 minutes. There, so they increase. Okay, you can see something dramatic happen there. They increase temperature. Now, which reaction or reactions show an increase in rate at time 10 minutes? Choose from forward, reverse, or both forward and reverse. Well, we just look at the graph. Which one is increasing? Definitely the forward reaction is increasing dramatically, but also the reverse one is increasing. So then that means our final answer therefore is both. Both of them are increasing. And then it says, is the heat of reaction, the enthalpy for the reaction, positive or negative? Fully explain. Okay, so this one, let me do it this side. If you remember the Chatelier's principle slide. I don't know what to do. I'll fix it for my next video. It won't do this anymore. Just gotta bear with it a little bit. Okay, so first of all, if you look here at the graph, all right, I just want to write this side. If you look at the graph, okay, we can see that the one that is favored the most is the forward reaction. Okay, so the forward reaction is favored. Okay, so we can see that, and we know that by Le Chatelier's principle as well, that actually an increase in temperature, if you increase temperature, an increase in temperature always favors the endothermic reaction, because remember, endothermic, it absorbs energy, it doesn't give off energy. So if you increase external energy, it's gonna absorb it the more and produce more. All right, and we know also by principle that the endothermic has the endothermic has a positive enthalpy, has a positive standard, a positive enthalpy. Well, if you don't know what enthalpy is, it's exactly what they're asking for, the change in H. Put it in that. Okay, so that's it. Therefore, we can conclude then and say, therefore, is the heat of reaction, therefore, the heat of reaction or change in H is positive. That's it. That's all we gotta say. Well, we are done for now. This was a very long question. I think it was worth something like 19 or 20 marks, somewhere there. Very long question. So make sure you understand this topic when you are preparing for your exam. Well, that's it from me. Thank you very much, and I will see you next time.
Hello everyone and welcome back to MV Tutors. I'm Tsolo and we are still doing the chemistry paper. I'll be looking at question 7 with you guys. So yeah, without wasting any time, let's get right to it. Okay, guys. Yeah, what do we have here? So, learners prepare a solution of known concentration by dissolving 2 grams pure sodium hydroxide crystals, or NaOH, sodium hydroxide, in water in a 250 cubic centimeter volumetric flask. Okay, so there you have your crystals, and you dilute them in water, or rather put them in water, and you have a solution. Okay, so now 7.1 asks, write down the term of the underlined phrase. So the underlined phrase says a solution of known concentration. Okay, guys, this is more of your theory. So you know that if you have a solution of known concentration, then it means you have a standard solution. Okay, so that's pretty much what they are looking for there. Standard solution. Alrighty. Then they ask, calculate the concentration of the sodium hydroxide solution. So how do you calculate concentration? Well, first of all, you have your formula there, which is C for concentration is equal to N over V. So N is your number of moles measured in mole, and V is your volume, but it is measured in cubic decimeters. Okay, so they gave us in cubic centimeters. We need to convert it to cubic decimeters, and to do that, you just take your cubic centimeters, divide them by 1,000, and you get your cubic decimeters. Okay, so yeah, let us get the concentration of sodium hydroxide. First of all, we need to get the number of mole. Okay, we already know that our volume is 250 cubic centimeters. Okay, so yeah, let's get the number of moles first. So it's sodium hydroxide. Okay, but firstly we need to get the molecular weight, okay, or molar mass of sodium, of oxygen, and hydrogen. Okay, so sodium, oxygen, hydrogen. I already know oxygen is 16 gram per mole. I know hydrogen is 1 gram per mole, but I'm not sure about sodium. So let's go and check. Okay, so sodium should be here on the first group. So sodium is actually 23. Yeah, 23 grams per mole. Okay, so the total then for sodium hydroxide, 1 plus 16 is 17 plus 23, that is 40 grams per mole. Okay, so that's just a little side calculation we do there. Okay, and then they told us 2 grams of pure sodium hydroxide. So we have 2 grams. Okay, and we're going to multiply. Remember, your molar mass is in grams per mole, but because we want mole as our final unit, we're going to have it in our numerator so that the grams can cancel out. So we have 1 mole, and we already calculated that we have 40 grams. Okay, so the grams are going to cancel out, and you will have 2 over 40 mole, which is the same as 1 over 20 mole. And if a half is 0.5, then 1 over 20, it'll be 0.05 mole. Okay, so there we have it, the number of moles for sodium hydroxide. Now we have our moles, and we did say that our volume needs to be in terms of cubic decimeters. So that's actually 0.25 cubic decimeters. Okay, so we are good to calculate our concentration. So the concentration of sodium hydroxide is equal to number of moles, which is 0.05, and the volume, which is 0.25. Okay, yeah, you can put your units there. Bend that. All right. So let us see. Okay, we have 0.05 all over 0.25, and the answer is 0.2. Okay, so we have 0.2 mole per cubic decimeters. Okay, so that is it. That is 4 marks. Nice 4 marks. All right, now let us go to 7.2.2. Now they want the pH of the solution. Okay, guys, you have sodium hydroxide. That is a strong base. I'm expecting the pH to be higher than 7. If I get anything less than 7, then there's a problem. Okay, so there are several ways, 2 ways actually you can calculate the pH. One way is if you have the concentration of your hydronium ion, then great, you can get your pH, okay, and you can go and calculate it. All right, the other way is if you have, okay, so there's POH, okay, that would be now the concentration of your hydroxide ion, okay, but when you're done, remember you're gonna get your POH, which is equal to whatever. Then for you to get pH, you know that pH plus POH is actually equal to 14. So pH will then be 14 minus your POH. So it's really up to you guys. Do you want to go the POH route or do you want to just go straight to pH? But the thing though, if you go straight with pH, you don't have the concentration of the hydronium ions, you have the concentration of your hydroxide ions. So from your theory, you would note that the concentration of hydronium times the concentration of hydroxide, it's actually equal to 1 times 10 to the power minus 14. So if I want the concentration of my hydronium ions, I will simply say 1 times 10 to the power minus 14 all over concentration of the hydroxide. So let's just do it both ways, okay? Let's just get the answer both ways so that at least you know in an exam which way you are comfortable with. Okay, so I know we got the concentration of sodium hydroxide. So does it mean the concentration of sodium hydroxide is equal to the concentration of the hydroxide ions? Yes, it is. Because sodium hydroxide is a strong base, it dissociates completely. Okay, so therefore the concentration of sodium hydroxide will be equal to the concentration of hydroxide ions. Okay, so that's just one thing to put out there. So that will be divided by 0.2. Okay, and we'll get our concentration of the hydronium ions. On the other hand, we're doing this simultaneously, guys. We are saving time. Okay, so log 0.2. Okay, so we're going to just pop out the calculator and see what we can work there. So we have 1 times 10 to the power minus 14 divided by 0.2, which is 500 times 10 to the power minus 16. Okay, and then we also had negative log 0.2. Okay, and that is 0.698. If we were to round up to 2 decimal places, do you see we're actually going to get 0.7? Okay, so yeah, our answer is 0.70. And then we can actually get the pH from here. And let me just write the pH calculation. So I have negative log 500 times 10 to the power minus 16. So yeah, we can get the pH. So if I say 14, oh gosh, okay, equal to, okay, so if I say 14 minus the answer, I'm going to get 13.30, and that is our pH, guys. It is higher than 7. It is quite close to 14, meaning we have a very strong base. Like I said, strong base that dissociates completely, so we are happy. But let's try it on the other end as well. If I have negative log 500 times 10 to the power minus 16. Okay, again, we have the same answer, 13.3. So both ways work out. It is really up to you which one you prefer, which one will be quickest, and which one you understand better. Alrighty, so now we get to the other part. So it says, the learners now react 1,5 gram of pure calcium carbonate with 50 cubic centimeters dilute hydrochloric acid of unknown concentration. Alright, the excess hydrochloric acid is neutralized with 25 cubic centimeters of the sodium hydroxide solution that they prepared. Okay, so this, the sodium hydroxide that they prepared previously, okay, we know that concentration, I think it was 0.2 mole per cubic decimeters, so we're good there. And then they gave us the balanced equations of the reactions. They were nice in balancing it for us. And the question says, calculate the initial concentration of the dilute hydrochloric acid. They're talking about the initial one day before reacting it with the calcium carbonate. So let's just put it in steps. So initially, you had your hydrochloric acid, okay, without anything happening to it, okay? So they want the concentration of this hydrochloric acid before it reacted with the calcium carbonate, before it even, what's happening? Yeah, before the excess was now added with the sodium hydroxide that we prepared. Okay, cool. So you had your initial hydrochloric acid, ne? Then you took 1,5 grams of pure calcium carbonate and you diluted it, or you added it rather, to 50 cubic centimeters. I'm just going to put it in brackets there. It's actually 0.05 cubic decimeters. Okay. You added it to the dilute hydrochloric acid of unknown concentration. Okay, so it's this one, basically, with the unknown concentration. And you remember that concentration is equal to number of moles over volume. All right. And then, lastly, okay, so basically this was the initial phase. I'm just going to say 1. This is the initial phase, okay. This is what happened initially, and then this was the reaction once you then had it with calcium carbonate, and then lastly you take the excess. Okay, now you're using your excess hydrochloric acid. Okay, so in that case, your excess hydrochloric acid, you neutralize it with 25 cubic centimeters, yes, or 0.025 cubic decimeters of the sodium hydroxide. And remember, the sodium hydroxide, its concentration was 0.2 mole per cubic decimeters. We know that concentration. Okay. So now what are we going to do? I'm thinking I'm going to work from the bottom all the way up. Okay, so I'm going to start at 3, then go to 2, then go to 1. Okay. So I'm going to calculate the number of moles for sodium hydroxide. Remember, there's an equation that they gave us. Okay, let me write it down. We have hydrochloric acid in aqueous solution plus sodium hydroxide, also aqueous solution, and then you have the salt, sodium chloride plus water. Okay, and it's already balanced. Okay, so I'm going to now get the number of moles in this equation, okay, for the sodium hydroxide. The number of moles, okay, so if concentration is equal to number of moles over volume, the number of moles is going to be concentration times volume. Okay, we already know the concentration is 0.2 mole per cubic decimeters, and we know the volume. They told us that the volume is 0.025 cubic decimeters. Remember, we're working with cubic decimeters. Okay, now let us see what the answer would be. So 0.2 times 0.025, and that is 0.005. Okay, so we have 0.005 mole. Now, if you look here, the coefficient of, or the number of moles for hydrochloric acid is actually 1. Number of moles for sodium hydroxide is 1. So it's a 1-to-1 ratio. Therefore, the number of moles for sodium hydroxide is equal to the number of moles of hydrochloric acid, which is both 0.005 mole. So, yeah, we have the number of moles for our hydrochloric acid, the excess hydrochloric acid. Okay, now we're going to go a step higher. Okay, now we're going to go look at the reaction. Okay, where that initial hydrochloric acid was actually reacting with calcium carbonate. Okay, we want to get the number of moles for the hydrochloric acid in that solution. Okay, in that reaction. Okay, so we have our first case here, the excess, and now we're going to look at the reaction. Okay, so this is the excess, and now we're going to look at the reaction. Okay, so we had 1.5 grams. Okay, 1.5, let me just shift this up. 1.5 grams of calcium carbonate. All right, and 1.5 grams of calcium carbonate. Okay, cool. So now I'm going to have to get the number of moles for calcium carbonate. Okay, so let's see for calcium, for carbon, for oxygen. Oxygen, we already know it's 16. For carbon, it is 12 grams per mole. Okay. And for calcium, I am not sure. So let's go and check. Okay, so calcium group 2, it's 40 grams per mole. Okay, so if we were to add all of that up, okay, we are going to get 40 plus 12 plus 3 times 16. So, oh, we have 100. Wow, okay. We have 100 in total, 100 grams per mole. Okay, so now I want to get the number of moles for calcium carbonate, which is equal to 1.5 grams times 1 mole, or over 100 grams. Okay, and 1.5 divided by 100. 1.5 divided by 100, that's 0.015. So that's the number of moles for the calcium carbonate. Okay, but we are looking for the number of moles for hydrochloric acid. So if we're going to write down the reaction, we have 2 moles hydrochloric acid plus 1 mole of calcium carbonate, and that gives us the salt, calcium chloride, plus carbon dioxide, plus water. Yeah, so whenever you have a carbonate and you mix it with an acid, you will get a salt, water, and carbon dioxide. All right, so you can see here, we have 1 mole. Okay, so we had the 0.015 mole of calcium carbonate, ne? And then it's time to We want to get how many moles there are for hydrochloric acid. So here we have 1 mole of calcium carbonate. And you can see that we have 2 moles of hydrochloric acid. So at the end, the calcium carbonates, they cancel out. So you have 0.015 times 2, which is 0.03 mole of hydrochloric acid. Okay, so great. So now for us to get the initial, which is what they want to know, the initial concentration, I'm going to say, so the number of moles for hydrochloric acid initially, it's going to be the excess amount plus the reacted amount. So before there was any reaction and there was some left over, there was the initial amount. Okay, so we're dealing with number of moles. For the excess, we had what? We had 0.005. Okay, and for the reaction, okay, we have actually 0.03 mole. So if we add that up, we can have 0.035 mole of hydrochloric acid initially. Now we can get the concentration, guys. We're almost there. So the concentration of the initial hydrochloric acid, or rather dilute hydrochloric acid, moles over volume. Okay, so the number of moles, we have that as 0.035. And the volume, which volume are we going to use? They told us that the learners now react 1.5 gram of pure calcium carbonate with 50 cubic centimeters of dilute hydrochloric acid. So we're going to go with 50 cubic centimeters, which is 0.05 cubic decimeters. Okay, and then our answer will be, so we have 0.035 divided by 0.05, which is 0.7, and that is the initial and that is the initial concentration of the dilute hydrochloric acid. Okay, so we are done. So yeah, we are done, but you could have actually done it another way. Okay, instead of adding all the moles at the end, what you could have done is calculated the concentration for the excess. We started off with the excess, right? Once you got your number of moles for the excess step, you could have just calculated the concentration there. So the concentration here would be number of moles, 0.005, all over the volume. The volume will still remain 50 cubic centimeters, or 0.05 cubic decimeters, and your answer here would have been 0.1 mole per cubic decimeters. Okay, so that's for the excess scenario. And now for the reaction, once you had received or gotten your 0.03 mole, you could have calculated the concentration there as well. 0.03 mole over 0.05. I'm going to use the calculator. I'm not sure what the answer will be, but 0.03 over 0.05, and that's 0.6. So you'd have 0.6 mole per cubic decimeters. And then if you wanted your initial concentration, you would have said the excess, which was 0.1 plus the reacted, which is 0.6, will ultimately give you 0.7 mole per cubic decimeter. Okay, and that is it, guys. Yeah, we answered the question fully. 8 marks, that was a lot, but you had to think. And I think, guys, in an exam situation, don't panic. Just look, what do you have? What information have they given you? Can you work back from the top to the bottom and from the bottom to the top? Like, just really think about what is going on. Think about the experimental setup and ask yourself, okay, if I were to do this using a procedure or whatever, what would I expect? Okay, don't just start writing things and now you're lost and you're like, what am I looking for exactly? So just take it step by step. If you see this is gonna waste time, go on to other questions and come back. Hopefully you have time to just think about it before you attempt it. Okay, but that's it from me. Enjoy the rest of your day, and yeah, bye. Hello everyone and welcome to MV Tutors. My name is Solo and I'll be looking at question 8 with you guys. So we're still on the paper 2 of physics, chemistry paper actually. So yeah, let's get right to it. Okay, so question 8. When a piece of sodium metal is added to water in a test tube, hydrogen gas is released. When phenolphthalein indicator is added to the test tube, the solution turns pink. Okay, so before we even answer any question, what is happening here? Okay, so you have sodium metal, right? I'm just gonna write on the side what it is that we have. Okay, so we have sodium metal, okay, and it is added to water. Okay, so there we have water, a liquid. Okay, and in that reaction, hydrogen gas is released. Okay, now we have hydrogen gas. And then what happened to our sodium? What happened to the oxygen? So at the end, okay guys, so the other product formed here, what really gives me an idea of what it is this indicator. So phenolphthalein, this indicator, when there is a presence of a base, okay, so it's an indicator. As soon as you put it inside, let's say in this case the test tube, you put this indicator and it turns pink, or worst case it turns red, then you know you are dealing with a base solution. Okay, so yes, phenolphthalein, normally if you have a base, strong base, maybe pH between 8 and 10, then you know you're dealing with a base there. Okay, so now the final product here, I'm expecting to have sodium hydroxide. Okay, let me just shift this sheet. Okay, I've lost my cursor. Found it again. All right, so we have sodium hydroxide, which is quite a strong base. Okay, and that is in aqueous solution. And yeah, I haven't balanced this equation, but I just wanted to see what is it that I have, so that going forward I know how to answer the questions. Okay, so now let's get right to the questions. So it says 8.1.1, define the term reduction in terms of electron transfer. So for those of you who watched the recording, what is it? The Saturday live sessions, you would know from question 9 that we talked about reduction and oxidation. So the term reduction in terms of electron transfer. So if something has been reduced, it means that electrons are added to it. Okay, so there's a gain of electrons when something is reduced. If something is oxidized, then there's been a loss of electrons. Okay, so for 2 marks, reduction, just gonna write it down. Okay, 8.1.2. Okay, no, we're at 8.1.1. Sorry about that. Yeah, I keep losing this cursor. Okay, so oh gosh, really? Sorry guys. I finally found the cursor. I keep losing it. I don't know why. Alright, so we are back. So 8.1.1. So reduction, basically, that is the gain of electrons. Okay? So gain of electrons. Okay, and then 8.1.2, it says write down the reduction half reaction. Okay, so what happens again here? You put sodium metal in water and then hydrogen gas is released. Okay, so in that case, if we look at this equation again, really our focus is going to be on this portion here with the hydrogen gas. Okay, so that part there has been reduced. Okay, that's our reduction, and we're gonna consult our table. 4A or 4B, it doesn't matter, but let us see. Okay, so can anybody see? Yeah, I think I have increased it enough. So let us look for hydrogen, water. Okay, let's start from the top. Okay, I'm not seeing anything. Oh, there we go. Okay, so we have, no. This is not it. This is H2O2. Okay, as we keep on looking. All right, so the more you do of these examples, the better you become at recognizing where you are, unlike me here getting lost. So there you have water, okay, and the product there you have hydrogen gas, and you also have hydroxide. Okay, so this is what we are going to take to the other side. All right, so there we had it. We had H2O, okay, and then we added some electrons because it got reduced. And then I don't know if you saw in the table, but there we have a forward and a reverse reaction. Okay, in this case, guys, the gas is gone. Okay, it's not in a closed system where you can then say you have a forward and a backward reaction. It's just going to be a forward reaction in this case, okay, because the gas, really, hydrogen is gone in the air. So yeah, please be careful if you do put the forward and backward arrows there showing that it's a forward and backward reaction. They're going to give you 0. So be very careful of that. Okay, so yes, we have water there plus the electron because it's being reduced. Then you're going to have hydrogen gas. And you're going to have hydroxide there, hydroxide ion. Okay, yeah, we can just go back to the table and see whether it's balanced or not. In this case, it is not balanced because here you have 2 hydrogens. Actually, this side, on the product side, you have 3 hydrogen atoms and 1 oxygen atom. Here you have 2. Okay, so if I were to add 2 here, and I see I have 4 hydrogen atoms, so I'm going to put 2 here so that I also have 4 hydrogen atoms, and I have 2 oxygen atoms on both sides. And in this case, because we have 2 minus, you know, so we should also put a 2 there. And we can check just quickly if we did. Yes, we have 2 water molecules, 2 electrons, 2 hydrogen gas, which is a diatomic molecule, and 2 hydroxide ions. So we are good. Okay, now let's go to the next question. 8.1.3. It says, write down the balanced equation for the reaction that takes place. Okay, guys, I'm just going to label that as 8.1.3. I had already started writing the equation. I just hadn't balanced it yet. So let us balance. So here we have 1 sodium atom. 1 as well, and then we have 2 hydrogen atoms. Here we have 3. Okay, similar situation as the bottom here, so we're just going to put it to this side. Okay, now we have 4 hydrogen atoms, so we're going to have to put a 2 there as well. We have 2 oxygen atoms, and we also need 2 sodium atoms. Okay, and then we have our balanced equation. That is a nice 3 marks. They were generous. And now 8.1.4, give a reason why the solution turns pink. Okay, so the solution turns pink. I did say, guys, you normally use an indicator called phenolphthalein because, you normally use that indicator, or rather, when you use that indicator on bases, it turns from clear to red as the worst case scenario. Here, it turned pink, so it was on its way to red, right? So now they're saying, give a reason why the solution turns pink. It's because it was in the presence of a base. Okay, so you had a base there. Okay, and that base was sodium hydroxide. You could say hydroxide. It's up to you, really. You could either say sodium hydroxide, or you could say it's because of the hydroxide ions. Okay, so that is why it turns pink. Okay, now cool, let us move on. And then we have, so now when a piece of copper is added to water in a test tube, no reaction is observed. Okay, so what do we have? We have a piece of copper, okay, also a solid, okay, and then we have water, a liquid, and they say no reaction occurs. Okay, so nothing, no products are formed. You just have the reactants but no products. So now 8.1.5 says, refer to the relative strengths of the reducing agents to explain why no reaction is observed. Okay, so yeah, refer to the strengths, relative strengths of the reducing agents. Okay, guys, so when you're gonna look at that, the table 4.4a, 4b at the back of your, or at the information sheet, it really does help you. Okay, so we're gonna compare. So you have copper there, okay, and we have water. Now we're gonna see what are the strengths of the reducing agents. Okay, so copper has a charge of 2 plus. Okay, it has lost some electrons. Okay, so it is going to bond. If maybe in that test tube you had an electrolyte, a cathode that is, then copper would go to that cathode. Cathodes are negatively charged, right? So yeah, but if you look at copper, okay, that is, yeah, copper being reduced. And then when you look at H2O, okay, water, H2O produces H atoms, okay, so H ions actually, and also hydroxide ions. Okay, so the hydrogen is what gets reduced. So basically you're going to compare copper and hydrogen. We're going to have a look to see which one has, or rather what are the strengths of the reducing agents. So copper 2 plus and hydrogen plus, what is actually going on with those. Okay, so here we have hydrogen. Okay, and as we can see, this table here, it actually shows the increasing reducing ability. Okay, so we're going to compare hydrogen with copper 2 plus. Okay, so where is copper 2 plus? There it is. So you can see that actually copper has a lesser reducing ability. It is weaker. It's a weaker reducing agent, okay, as compared to hydrogen. Okay, so hydrogen is stronger than copper. Okay, so now let's go back. So we can see copper, that's actually a weaker reducing agent. Okay, and as a result, okay, because copper is the weaker reducing agent to hydrogen, and water by itself, water rarely gets reduced. So now you have something that's weak. Copper is like a weak reducing agent. and water in itself rarely ever gets reduced, there won't be any reaction. It's just not going to happen. So that is why then you don't see or you don't observe any reaction. You need to refer to the strength of the reducing agents. We know that copper is a weaker reducing agent than hydrogen, but in general, water does not reduce. So no reaction will be observed. Okay. And then, yeah, now consider the cell notation below. Okay, so we have lead. Okay, then we have this straight line, and then we have the iron, lead 2 plus. Okay, so that's the solid, and that's the iron. And then again, you have the ions. Oh, we have a double. Yeah, double lines there. Then we have our ions, and then we have platinum. Okay, now it says, what does the single line in the cell notation above represent? Okay, so what does the single line represent? Okay, so 8.2.1, that single line is actually like a division. Okay, okay, so you have your double. So yeah, let me just rewrite it here. So we have lead and then a single line, and you have lead 2 plus the iron. Okay, then we have the double line. Okay, then we have iron in aqueous solution. Okay, then we have iron 2 plus. Then we have platinum. Okay, so this side of the double, on the left side of this double line, that's where you actually have your anode. Okay, and on the other side, that's where you have your cathode. Okay, that's just with the double lines. Now with the single lines, this side, that's where you have your electrode. Okay, that's a C there. And this side, that's where you have your electrolyte. Okay, here you have your electrolyte. And again, your platinum there, that's your electrode. Okay, so this line here, the single line, that represents like a division. It is a phase, what do we call, what's that term? Yeah, it is a phase separator, because here you have a solid, okay, it's in solid phase, and there you have aqueous solution. Okay, it's like liquid phase, sort of, it's in solution. So the single line represents a phase separator. Okay, and then 8.2.2. Okay, let's just raise it up. Okay, 8.2.2, state the energy conversion that takes place in the cell. All right, so now, how do you know? First of all, what kind of cell do we have? The fact that we have double lines here tells me that I have a salt bridge. That is an indication of the salt bridge. Okay, and if I have a salt bridge, then it means I have a galvanic electrochemical cell. Okay, it is galvanic, right? It is a galvanic cell. So in that case, when they say state the energy conversion that takes place in this cell, well, we know that it is from a chemical. Sorry, just erase that. Okay, so it goes from chemical energy, okay, and it transfers to electrical energy. Okay, and then 8.2.3. All right, so it says calculate the initial EMF of the cell under standard conditions. Okay, so under standard conditions, the equation, you get that off your formula sheet. So the EMF of the cell, let me just read off the formula sheet. It is E of the cathode, okay, minus E of the anode. Okay, and we know our anode, that's where we have the lead 2 plus, and our cathode, that's where we have iron 3 plus going to iron 2 plus. So we're going to refer back to our tables and we're going to check what those E values are. Okay, so remember on a galvanic cell, you would have your voltmeter attached to it, and basically the E there, or the EMF, it's actually called electromotive force. Yeah, so the EMF there gives you the voltage. All right, so when you get the difference between the cathode and the anode, then you're going to actually get the reading you're going to see on the voltmeter you've attached to your galvanic cell. That is what we're actually calculating for. Okay, so let's have a look. All right, it was lead, right? Oh, there is lead. Nice, it's close by. So that E value is actually negative 0.13. Okay, so that was actually the anode, negative 0.13. Okay, so I have a value here, minus negative 0.13. And then I'm going to go look for iron 3 plus, which goes to iron 2 plus. Okay, let's go see where that is found. Okay, so we have iron here, but no, that's not the one that we are looking for. Okay, let's just go to the bottom and check. Nope. And then we have this iron here. Nope, that's not the one we're looking. We're looking for the one where it goes from 3 plus to 2 plus. Okay, and yes, there it is. We found our value there. Okay, and that answer is 0.77. Okay, so our value there, it's actually 0.77 minus 0.13. So that's actually 0.77 plus 0.13. Okay, so the 7 and 3 become 10. And then we carry over, we have 2 plus 7, that's 9. Okay, so we have 0.9 volts. Okay, and that concludes question 8. If you have any questions, any comments, please do put it in the comment section and we'll try our best to answer you. If you would like a session, please do go to our website www.mvtutors.co.za and make a booking with us. Otherwise, you can WhatsApp us on 076-312-1107. All right, enjoy the rest of your day. That's it from me. Good morning, everyone. I'm Tilo, and I'll be looking at question 9 with you. All right, so I hope you enjoyed the session with my husband for question 10. We're going from the back, moving forward. Okay, so yeah, don't be phased. All right, guys, so yeah, what is it saying? So question 9, it says, the diagrams below show 2 electrochemical cells in which carbon electrodes are used. In cell A, concentrated copper 2 chloride solution is used, and in cell B, liquid aluminum oxide is used. Okay, guys, let's just go through that again. So you have 2 electrochemical cells, okay, and these electrochemical cells have batteries, okay, as you can see there, batteries with the longer side indicating positive and the shorter side negative. Okay, and then in which carbon electrodes are used. So carbon, guys, it's actually a good conductor of electricity. So that's why they normally use carbon electrodes. And another thing is that it has a higher melting point. So even if your reaction is like getting hot, it will take a long time before it melts. Okay, so it's quite good to use. And then they say in cell A, you have concentrated copper 2 chloride solution. Okay, you can see there, aqueous solution. What does that tell you? You probably had your copper 2 chloride in solid form, okay, which was granules or powder or whatever, and you mixed it with water. Okay, so definitely add it with water there because it's a solution, right? And yeah, so that's just one thing I wanted you to note. And as a result, guys, because of that, you're gonna have, so this copper 2 chloride, you're gonna have chlorine ions in here. Okay, let me end it. Oh no, let's start again. Okay, so you're gonna have your chlorine ion or chloride ions. Okay, then you're gonna have your copper 2 plus ions, and then guys, there's also H2O. Okay, so you're gonna have hydrogen ions in there as well as hydroxide ions. So cell A is quite loaded. Okay, so please don't forget, when you have an aqueous solution, you probably added water. Okay, and then in cell B we have liquid aluminium oxide. So this is just purely aluminium oxide, there's no water added to it. So the ions that will form, or it will dissociate into aluminium 3 plus, and you also have oxygen 2 minus. Okay, those are the ions that form. All right, and of course aluminium oxide is actually in its melted state, hence it is a liquid there. All right, so yeah, that's just one thing to be aware of. And now let us answer the questions. So they're asking here, what type of electrochemical cell, electrolytic or galvanic, is shown above? Okay guys, so you have a battery. I was kind of hinting there. So you have a battery there, okay? And we can see that when you have a battery, so you're gonna have electrical energy, okay? Electrical energy actually converting to chemical energy. Okay, so you need to have current there. A battery will provide your electrical energy there, having, okay, so it moves from the positive side to the negative side, so you'll have your electrons actually moving from the positive to the negative side. So you have electrical energy converting to chemical energy. This chemical reaction cannot take place if you don't have a battery source there providing electrical energy. Okay, so yeah, therefore we're going to go with electrolytic electrochemical cell. That's the type that we have. Okay, and that's your 2 marks. And now, so I want us to note something. So you have your electrons going from the positive side of the battery to the negative side. Okay, so if electrons are leaving on this side, then you know this electrode here, it's actually being oxidized. Okay, and I don't know if you know the acronym oil rig, so I'm just going to say oxidized here, and then it means that this cell here, this electrode, it's actually reduced. Okay, so yeah, the oil rig I was talking about, oil rig, basically it's saying oxidizing is the loss of electrons, so that I there is just is. So yeah, oxidation is the loss of electrons and reduction is the gain of electrons. So here you see this electrode is losing electrons, and if it's losing, then it becomes positively charged. Okay, so here you have your anode. Okay, and then your electrons are rushing over to the right. Therefore, this electrode is negatively charged, and that would be your cathode. Okay, so you have a cathode this side, anode that side, and then, interestingly enough, on your positive electrode, your negatively charged ions, your N ions, are gonna stick there. So chlorine is gonna come and stick all the way there, and also your hydroxide is gonna come all the way there. Okay, and on the other side, when you have a negatively charged electrode, the copper 2 is actually gonna stick itself there, as well as the hydrogen ion. Okay, so that's basically what's happening here. Even this side, okay, same thing. Yeah, basically a repetition. So this side you have your positively charged electrode, which is your anode, and this side you have your cathode. Okay, your aluminium will go towards the cathode, whereas your oxygen ion will go all the way to the anode. Okay, cool. Now they are asking here, okay, in 9.2.1, write down the half reaction that takes place at the anode of cell A. Okay guys, this is the anode, right? Now there are two, you have your chlorine there, and you also have your hydroxide. Okay, so I'm just gonna, let's just put it to the side. Let me reduce this, and let's just talk a bit. Are you guys still coping there? Okay, so basically at your anode there are two half reactions you can write, okay? One for chlorine and the other for the hydroxide. Okay, but they only want one, so meaning you can't write both. Okay, you need to decide which one it would be. Okay, they did not ask about the cathode, but I'm gonna put it there just in case, so that you know if next time they ask about the cathode, you are well prepared. Okay, so at the cathode, what's gonna go there, it's your copper, okay, and also your hydrogen ion. All right, and to assist you with the half reactions, you're going to look at table 4A and 4B on your question paper. Okay, and guys, so at the anode, that is where oxidation happens. So which one between the two is likely to be oxidized? Like I said, you can't write both these half reactions, you need to write only one. Okay, so out of these two, which one is likely to occur? Which one is likely to oxidize between the two? Well, there are two ways of actually figuring that out. So if you have a dilution or a diluted mixture, okay, then the hydroxide is the one that's going to be oxidized, okay? But if you have a concentration or concentrated solution, concentrated solution, okay, then in this case your salt, or no, not your salt, chlorine or bromine or iodine, that is what will be oxidized. Okay, so it depends. And in this case they told us that we have a concentrated solution, so definitely I'm going to write the half reaction of the chlorine, and we're going to use our table to actually see what that half reaction is. Okay, so like we said, for the anode, either if it's diluted, hydroxide; if it's concentrated, then it's either going to be your chlorine, iodine, bromine, whatever, your group 7 basically. Okay, now at the cathode, you ask yourself which one is likely to be reduced. Okay, so the one that's going to be reduced is the one that has the least reduction ability. Okay, and we're going to look, but let's have a look at chlorine and hydroxide. So we have our table here, 4A. Whether you use 4A or 4B, you're going to get the same result. So we said the one that is likely to be oxidized, okay, we're going to see here, this side it says increasing oxidizing ability. So the one with the highest oxidizing ability, that is what will be oxidized. And we had chlorine, we already determined it's going to be chlorine, but we had chlorine and the hydroxide. Okay, so let's look for it. Okay, there is chlorine, and that is the half reaction for chlorine, guys. That's pretty much your answer. Okay, your answer, you have your product that's produced there. You're gonna have chlorine gas, okay, and this side you're gonna have your chlorine ion, okay, and you have your electron that side. Okay, so in this case, this actually is gonna go that way. And if you balance it, you're gonna have 2 because you have Cl2 here. Remember, chlorine is a diatomic molecule. It comes in pairs, okay, because it needs to fulfill the octet rule. It can't just come as Cl, it has to be Cl2, okay, so that's a diatomic molecule. So you have Cl2, and because you have 2 of them there, you need to balance it with 2 and also put +2 there. Okay, so that is the half reaction that 9.2.1 is asking. Okay, and then you have the hydroxide. Where is there's the hydroxide there. So do you see that the hydroxide has a lesser oxidizing ability than the chlorine? Hence the chlorine is the one that will be oxidized. But when we look at the cathode side, you have your copper there, you also have your hydrogen. The one that's going to be reduced is the one with the least reduction ability, the least reduction ability. So we have our hydrogen there, and we're going to look for copper. Let me just increase this, and we're going to look for copper 2. Okay, so we have copper 2, but it's 1 electron. That's not the one we're looking for. Oh, there's the one we're looking for. So here you can see that the increasing reducing ability, it's going in this direction. My goodness. It's going downwards. It's increasing in the direction of downwards. Okay, so the hydrogen there has a higher reducing ability, but your copper has the lowest reducing ability, and therefore if they were to request the half reaction at the cathode, you would definitely go for copper. But that's not what they asked. They asked for the half reaction at the anode. Okay, so let's just go back and write that answer. Okay, so 9.2.1, the answer therefore, okay, you would have your chlorine ion there, okay, and then it goes, a gas is produced, chlorine gas, okay, and you have your electron there. But because, like I said, we need to balance the equation, we have 2 chlorine atoms there, the diatomic molecule, so you need to balance by putting a 2 there, and also 2. Okay, so that is your balanced half reaction taking place at the anode of cell A. Okay, so yeah, I took time in explaining this because I really want you to understand and get it, especially when you have a solution and water is involved. They don't tell you, they expect you to know. Okay, so yeah. Now 9.2.2, half reaction that takes place at the cathode of cell B. So basically we're looking at this aluminium there because it's sticking to the cathode there. Okay, so again, if you want to know what the half reaction is, your tables are there to assist you guys. You shouldn't be struggling. Okay, let us look for aluminium. Okay, right, there it is at the bottom. So aluminium is there. Okay, so we have the iron there. You see the iron, you're adding the 3 electrons because it has a charge of 3 plus. I don't know if you can see, it's quite blurry, sorry about that, but yeah, has a charge of 3 plus, hence you're gonna add 3 electrons there, and ultimately you're gonna get your metal, your aluminium metal. Okay, your aluminium metal is what you want basically. So you started off having your iron, okay, and because it's reduced, you're gonna have 3 electrons added to it, and ultimately you're gonna have aluminium. Okay, it is a solid, so this is aqueous solution, that's a gas. Here you have solution as well, and that is a solid. That is what will form, guys, at the end of the day with cell A, cell B. Cell B will producing, you'll have aluminium surrounding it there, the aluminium metal. Okay, so the electrolytic process there, you're really trying to get pure metal. Even this side with the copper, you're gonna get your pure copper that's gonna form this side. That is the whole process there. Okay, this process is quite expensive though, and it needs quite a lot of energy. So yeah, but that's 9.2.2. Now 9.2.3, write down the name or formula of the product formed at the cathode of cell A. We just spoke about it. So 9.2.3, that's actually copper. Okay, so it's a copper metal. Okay, I don't know how specific they want you to be, but yeah. And then now they're saying give a reason why the mass of electrode Y, okay, so your anode for cell B, it decreases after a while. So why does the mass decrease after a while? what is actually happening there? Okay, so we have stated that no, it's actually 9.3. So what is actually happening here, guys? Remember, your aluminium ion is going towards the cathode, and your oxygen ion is going to the anode. All right, and what is this anode made of? It's actually made of carbon. Okay, solid carbon. So basically now you have this chemical reaction going on. You have your ion, your oxygen ion, but I'm just gonna say O2 there, because oxygen doesn't just come by itself. It's also a diatomic molecule. And you also have the carbon there, okay, because they did say carbon electrode. And basically what you're gonna get is carbon dioxide. So carbon dioxide forms, okay, and that is a gas, so it forms bubbles. All right, so basically your oxygen, as it attaches to the electrode or to the anode there, it will eat away at it because your carbon and your oxygen form carbon dioxide, bubbles form, and they dissipate in the air basically, because of the carbon dioxide gas that forms. So now the volume or the mass of your electrode is going to reduce. So it was a perfect cylinder there, I think, or a square cylinder, whatever, and then now it's going to just reduce, and ultimately wither away. So for cell B, okay, when you have aluminium oxide, they normally say you need to replace your carbon electrodes a lot, because the oxygen keeps eating away at it, forming carbon dioxide gas. So that is the reason why the mass of the electrode decreases. You're going to refer to the chemical equation there, that you have oxygen and you have carbon, which forms carbon dioxide gas, which escapes in the air. Okay, and yeah, guys, that's pretty much it. Thank you for joining in this morning, and I hope that you learned something today. And please do ask questions, do comment, do give, I don't know, input how we can serve you better here on this platform. Otherwise, enjoy the rest of your Saturday. And yeah, that's it from us. Bye.
Well, good morning once again. It's me, Figure. I'm doing question 10. So just to show it clearly to you, there it is. This is the physical science, the chemistry part, which is paper 2. And you just wrote this exam a few weeks ago. This is the 2021 June exam. So, and remember, this is live, so we can interact live time. If you have any questions, ask them right now, or as we go throughout the session. We are actually monitoring the comments section so that we answer your questions as we go. All right, let's get right into it then. Question 10. Now it says here, the incomplete equations below show the 4 steps involved in the industrial preparation of sulfuric acid. This is in your textbooks, so I'm sure you've seen this. It looks very familiar. A and B represent 2 compounds. Okay, I can already tell what A is. But just in case you can't, that's what they're asking for. Write down the name or formula of compound A. So I'll get to answer you if this is a revision for you. So here we go. Compound A. Now, compound A, when you add sulfur and oxygen, you actually get sulfuric dioxide, like this. Okay, so this is what we call sulfuric or sulfur. Let's just call it sulfur, because I think that's the more correct answer. Dioxide. Sulfur dioxide. Right, now they want compound B. Compound B is SO2 plus oxygen, which gives us, if you said sulfur trioxide, you are correct. SO3, sulfur trioxide. Looks very familiar, doesn't it? Sure it does. This is one of the things they teach you in all the textbooks in metric to do. How to prepare sulfuric acid. Okay, and then it says the catalyst used in step 2. Okay, so it's a catalyst that's used here, a very common catalyst. If you said vanadium, then you were right. V2O5 is just standard. This one is called vanadium. Vanadium. Now, do you see that is 5 oxygen? So 5 is represented by pent. So this is pent. And then it's an oxygen, so it's pentoxide. Pentoxide. So vanadium, pentoxide. Ladies and gentlemen, that's what it is. And then the next question says the sulfuric acid formed in step 4 is used to prepare ammonium sulfate. Okay, now what's the question? The question is, write down a balanced equation for the reaction. Okay, so what's happening here is that we are taking the sulfuric acid, which is H2SO4. If you're wondering where I got this, it's right here. It's right here. This is it. That's it. Also, they told us there. That's what they're talking about here. Sulfuric acid is formed and it's used to prepare ammonium sulfate. So what are we going to add here? There's a clue in this sentence. If you said ammonia, then you're right. We're going to add ammonia. See, the sentence is very clear. You know, ladies and gentlemen, one of the very first defenses when it comes to answering questions is actually understanding the English, or understanding what the question wants. If you don't understand what the question wants, then you're not going to answer the right thing. So it's important that we understand the question, we take the clues that are in the question and use them to answer the question. Use them in formalizing whatever formula to get the question. So here they are talking about ammonium. So as a clue, we must add ammonia, and ammonia is given by NH3. Okay, so this, okay, so when we add these two, we are going to get, this is just theory as well, you should be aware that this is just standard. You get NH4. Now because SO2 it has a charge of 2 up there, so that's why we put this in brackets, and then we're going to put a 2 there, which comes from the 2 from the SO4. Okay, that's what we get. Now all that's left, now if you don't know how I came up with this, we do have a lesson. Just check out our YouTube channel where we teach some of these things, how they actually come about. But all that's left now is just to balance. Now when we balance, we often start with or rather we end with H, and the second last one is O, so we're gonna start balancing the N. Okay, so when we start with the N, we can see there's two of them here. Nitrogens is one, they coming, so it's 1 times 2. Okay, so because there's 2 this side, we need to balance this side. Let's see, how many do we have here? We have 1. Okay, so in order to get 2 of them, all we need to do is put a 2 there. So now our ends are balanced. The next thing that we want to balance, that is S. Let's look at S. We got 1 this side, we got 1 on that side, so we're cool. The next one then is O. Okay, we got 4 this side, we got 4 this side, balanced. Then the last one is H. We got 8 here because we got 4 times 2, which makes it 8. This side we have 2 times 3, so it's 6 plus 2 this side. Ladies and gentlemen, this equation is balanced, so we need not take it any more further. Okay, so let us just continue here with the next question, because we're done there. The next question says, write down a balanced equation of the reaction. We just did that. Oh, we are here now. The diagram below shows a bag of fertilizer. Okay, write down the meaning of NPK. Well, that's just theory work once again, but we're gonna write it. So N, as you know, represents nitrogen. Okay, and then what's the next one? And P represents phosphorus. Okay, phosphorus. And then the last one is K. Oh, now K is a weird one because it actually means potassium, and there's no K in potassium, so it's a weird one. That's the hard one. So NPK is just a ratio between nitrogen, phosphorus, and potassium that is in a fertilizer. Okay, that's the full meaning of it. And then they say question 2 says the bag contains 4 kg of ammonium nitrate. That's the formula, which is the only source of nitrogen. Calculate the mass of the fertilizer in the bag. Okay, so there's a picture of the bag and the fertilizer. Now write down on the comment section, just on the comment section, let me know, what does this 26 stand for? What is this 26? Tell me on the comment section right now if you know what it is. But let us continue with the question nonetheless. What are we supposed to calculate here? Calculate the mass of fertilizer in the bag. Okay, a bag contains 4 kg of ammonium nitrate, which is the only source of nitrogen. Okay, so it's the only source of nitrogen. So if it's the only source of nitrogen, we want to know what percentage of nitrogen is in ammonium nitrate. I hope you understood that. But in case you're watching the recording, you can rewind. For you who is live, what they are actually saying is that what we want to know is how much of nitrogen, okay, how much percentage of nitrogen is in ammonium, there we go, nitrate. And since we want a percentage, we'll need to multiply this with 100. Okay, so we need the atomic mass of this. So let's actually start with the atomic mass of NH4. Why did I just write 3? 4 and to do this we need the periodic table. So I did add a periodic table over here. Let me just zoom again. Okay, it's enough. First of all, we need nitrogen. There it is. It's 14. Okay, so we'll go back here and we're gonna write 14 plus, we know hydrogen is always 1. It's the first one in the periodic table, so it's 4 of them, plus we just got that nitrogen is 14, plus let's go check out oxygen. Now if you look here, you can see oxygen is 16. Okay, its atomic mass is 16, so we're gonna add 16 right here. Okay, ladies and gentlemen, we need a calculator now at this point, so I'm just gonna go grab a calculator. I forgot to add it earlier, so forgive me, I am sorry. What did I just do? I just switched it off. So in my calculator, I want to put 14 plus 1 times 4 is still 4, plus 14 plus 16. You get 48. Oh, wait a minute, I'm missing something. Why didn't anyone tell me in the comment section that I'm missing something? Okay, so I'm missing a 3 right there, which means I should multiply this with a 3. Okay, that's it. Alright, so we can go back now to our calculator and we're gonna say, okay, let's just go back to that calculation there and we put a times 3 there. We get 80. Cool. So that's 80. Okay, now we've just solved this part of the equation. Now we need to get this one. All right, so that one, as you can see, there's actually 2 of them here. We've got nitrogen there and we got another one there, and both of them are 14. So the nitrogen part then is therefore 14 times 2. There's 2 of them. 14 times 2, just from my head, is 28. So what does this mean for us? It means that we are actually going to say, let me just come this side because we had started there. We are going to say 20, let me do that again. 28 divided by 80 times 100. That, ladies and gentlemen, is going to give us the percentage of nitrogen that we're looking for. I need a calculator again. Here we go. So this is 28 divided by 80 times 100 to convert it to a percentage. That's 35%. Okay, that is just 35%. Okay, so 35% of ammonium nitrate is nitrogen. Okay, and we are told it's 4 kg of ammonium nitrate. So how does that help us? It helps us here, because now what we can do is take that 4 kg and say, okay, since 35% is nitrogen, then we can take that nitrogen, which is 4 kg, multiply it with 35%. 35% is just 35 divided by 100. Okay, percent just means divide by 100, but you already know this. This will give us the exact amount of nitrogen that is actually available in ammonium nitrate. So okay, so we need a calculator. Let's bring back our calculator. It's gonna be 4 times 35 divided by 100, 35%. Now I want it in this 1.4. Okay, so we get 1.4. This is 1.4 kg. So 1.4 kg is just nitrogen in this entire bag. Okay, now to get it, the question actually wants a fertilizer. To get the fertilizer, we need the phosphorus and the potassium added together. So what we're going to do to get those, we'll take this ratio here. This is the NPK ratio. Okay, so let's just take the NPK ratio. NPK ratio is 1. Let me just actually, okay, write the NPK for you. That's N is 2, P, so P is the ratio 3, and then the last one is 2, which what did I just do? The last one is potassium, which is 2. Okay, so watch closely what happens now. We just solved nitrogen, which is represented by 1, and it's 1.4 kg. So to get this ratio, what we're going to have to do is say 1.4 times 3. Okay, and then to get this one, then potassium, we're going to have to say 1.4, you guessed it, times 2. Okay, because those are the ratios. Well, if you wanted to apply it also on the end, it will be just 1.4 times 1, because that's the one. All right, 1.4 times 1 is just 1.4. I might need a calculator for this one, so let me get my calculator. That one is going to be 1.4 times 3. Okay, and we get that weird number. Let's change it to decimal. So it's 4.2. 1.4 times 2, that's gonna be 2.8. Okay, so all of these are in kgs, and we need the combination of them to get the final answer, which is the fertilizer that they're looking for. So we're just simply going to add them. 1.4 plus 4.2 plus 2.8. Okay, whatever answer we get here is actually our final answer. So let's just put it in a calculator. 1.4 plus 4.2 plus 2.8. That's it. That's it. Let's get it in decimal. 8.4. Okay, so that's our final answer. 8.4 kg is the amount of fertilizer in this particular bag. Now, if you didn't understand what just went on there, feel free to book a tutorial session with me, and I'll be glad to tutor you further in these matters. But if you did understand, then good for you. This is why we do this. I'm done with my session now, so take care, all the best, and I hope you understood. Okay.